and we'll get started from the current slide. Now, let's talk about what we're going to be doing today. We're going to start in chapter 16 and get as far into 16 as we can. Now, if after 2 hours in approximately, it looks like we might have time to finish it and do the lab, we'll go on and finish it and do the lab. If it doesn't, we'll continue, and let me see, is it Cole? I thought it was. If it doesn't look like we're going to be able to do the lab, I'll just go on and finish chapter 16, and then if there's not time to do the lab, we'll start on chapter 17. But the last 30 minutes will be the test on chapter 15, okay? So if you don't have your formula and equation sheet ready for 15, might be something to be working on there. So we'll see how it runs today. This is a fairly quick chapter, I think, but we'll see. Okay. Any questions on 15, since there will be the test at the last 30 minutes today, or anything else we've covered so far? Okay, is this Marcus? No.
Sure.
Huh?
Sure.
Chuck?
Yeah, Louis. Sure, Louis.
Louis?
Yeah, Louis.
Louis. You're Sean. I got you. I can't hear well. Okay. Okay. So for people who just came in, we're going to start on chapter 16, go a couple of hours there. If there's a chance that we can finish 16 and do the lab, we'll do that, because the lab is very short in-class lab. Most of the lab you'll be doing for the next couple of weeks or maybe longer at home, okay? We'll talk about that when we get there. But the last 30 minutes today will be the chapter 15 test. So that's what I started off. Any questions on 15? Okay. All right. The chapter 16 is Earth and Space. And let me also tell you this. This is not starting well. We're just barely, 2 weeks into the term. Fantastic. Thank you. And I'm already so far behind in grading. It's awful. Okay. Now, part of the reason for that is Monday's holiday. Normally I have 4 hours and 30 minutes, 4 hours and 15 minutes of office hours on Mondays. I didn't have that this time because it was a holiday and I was home. I got a few things done, but I didn't have any good solid 4 hours to work at home. So that's one reason. But the other thing is I'm teaching right now 9 classes, but there will be 10 this term. And I just don't have any time to grade. So I have to make time, and so far I haven't had good luck with that. Tomorrow I have 4 hours. I hope to be able to work on catching up grading, but we'll see how it goes. I already have 3 letters of recommendation I have to do tomorrow, and then do my grading. So it's been really tight already. All right. If there's no questions, we'll get started on chapter 16. Okay, reviewing. Chapter 14, the universe. Okay, everything. Then last chapter, 15, was the solar system. Okay, narrowed it down to our solar system. Now we'll be studying the Earth in space. Now, I don't like to call it this because this is actually the Earth and Moon in space, the Earth-Moon system in space. So that's what we're dealing with in this chapter. The first half, or part of the chapter, is going to be mostly talk about Earth-type stuff, and then we'll break off and do Moon-type stuff in relation to the Earth. Core concept here, the way the Earth moves in space is used to define time, we've already been dealing with that, and to describe location on the surface, we've been dealing with that, and causes other recurrent phenomena such as the seasons. I think we talked about those as well. We'll go into a little more depth now. Now here's another rather nice, pretty picture of the solar system. Still not very realistic as it comes to size and distance. The sun, of course, if it was its regular size, every one of these planets would be a little speck, and you would hardly be able to see them. Okay? So certainly there's that. And if we were to guess here, I would say this must be representing Mercury. And strangely enough, I don't know. I don't see either Mercury or Venus is missing here. Usually we think of the red planet as being Mars, but that's somewhere way in the background. This is obviously Earth. This looks to me to be the moon, okay? So we're on the moon taking a picture this way, which again is not very realistic. You can't see Jupiter that big from there. You don't see any asteroids in there. That's obviously Saturn, given away by the rings, and that would be Uranus and Neptune way out there. And those are not realistic because those are so incredibly far away, they wouldn't even be specks, okay? But another sort of attempt to represent the solar system. And it does a decent job, okay? So let's start with characteristics of the Earth. Starting with the shape and the size of Earth. Now, most globes that you'll ever see are usually approximately spheres, balls, okay? Earth is not really quite a sphere or a perfect ball. It's what they call an oblate spheroid, okay? Spheroid meaning it's a lot like a sphere, but not quite, okay? What are the deviations? Well, the oblate part means we're a little bit pear-shaped. Not totally, but we're a little thinner at the top and bulging at the middle, and the bottom. I can kind of relate to that. Now, this statement here makes no sense to me, but I guess it must be true. They say there's a lump in the Pacific. I think, well, if there was a lump in the Pacific, the water would roll downhill, wouldn't it? And it would be flat again. But obviously, it's not quite. I don't quite know how to describe that. And then they say there's a depression in the Indian Ocean. Well, it seems like if there was a depression in the Indian Ocean, water would be running into it. But again, that's maybe just me. But what they're saying is it's not a perfect sphere. Okay. Now, all these elevations and depressions, the deviations are less than 85 meters. And when you think about how enormously big the Earth is, 85 meters would be less than a football field in length. So from the maximum elevation that's out of round to the maximum depression that's out of round, the deviations are less than 85 meters. That's not very much, folks. Not very much at all. Okay? Now here's here's a picture of the Earth, and this is not a very fair picture. This makes it look like it's way off from being a sphere, but that's because this is in the dark. This is in the shadow here. That's not. There's the Earth, and it looks awfully close to being spheroid. You're not going to be able to tell it's not, I don't think. And I believe this picture is of North America right here. There's the Florida Panhandle, the Gulf of Mexico, the Yucatan Peninsula in Mexico. I think that's pretty much what you're seeing there, but it's hard to tell with all the cloud cover. But here's a drawing of what they're meaning. Now, which one of those is the sphere and which one is not? I swore when I first looked at this was the oblate spheroid, and then it is, okay, and that's the sphere, okay. But then when I looked at it a different way, I thought, no, this is the spheroid. No, it isn't. Okay, so we're a little narrow at the poles, not quite spherical, and sort of bulging in the middle, and that's what makes it. And if you think about it, spinning on an axis, it tends to throw things out in the middle and pull them in top and bottom. And sure enough. Now this is a gross exaggeration, because you see the difference between the maximum diameter this way and the maximum diameter that way is that looks like 42, it says here kilometers. There it says 85 meters. I can't quite, make sense of why those aren't quite matching well. But the point is, that's 42 kilometers out of almost 13,000 kilometers. That's not much difference, okay? So it's very, very little. And again, this is greatly exaggerated here over what the real difference is, okay? Almost a perfect sphere, but not quite. All right. Now, speaking of figures that aren't quite realistic, but at least you get relative sizes, this one's not far off, okay? Now, I can't tell by looking which is which. I have a feeling they mean this to be Mercury, that to be Venus, that to be Earth, and that to be Mars. Of course, they are not that close together, but this is just showing the relative sizes, okay? Now, because Mercury is closer to us, it looks bigger than Mars, but it's not. It's smaller. Because Venus is closer to us than Earth, it looks bigger than Earth. It's not. They're close, but not quite. Earth is larger. But this is the amazing thing. If those were the relative sizes of the inner 4 terrestrial planets, Mercury, Venus, Earth, and Mars, that's Jupiter in the background. Look at the size of that thing compared to the 4 terrestrial planets. I mean, we're minuscule. Mercury is actually smaller than 2 of Jupiter's moons, so it just gives you an idea. Saturn is huge as well, not as big as Jupiter, and then there's Uranus and Neptune out there, almost the same sizes, but the distances here are nowhere close to being real. But that's a pretty interesting photograph with the relative sizes in mind. Okay. Sorry, I just saw that. It has nothing to do with what we're talking here. All right. Now, before we move on to motions of the Earth, here's another slide here, a figure here that we don't have a slide. And this is the planets appear along the ecliptic in the sky because the planets orbit the sun very nearly the same plane. So this is sort of more descriptive, but just this gives you a general idea. The ecliptic is the sun's path, so the planets are not going to be far from the sun. Okay, there's Mercury, though you'll hardly ever see it, and that would be in, I don't know what year this was supposed to be. They don't list that here, but this was near June, perhaps. Mercury was just barely visible. Jupiter, right on the ecliptic almost, that is almost always visible. That was, before July, late June. Here is Regulus, which is a star, not a planet. There's Mars over here in between September, October type time frame, near the ecliptic. Spica is a star. Saturn here. Saturn's pretty tiny. You might see it, but you never realize you're looking at a planet. Antares is another fairly bright star that's pretty close to the ecliptic, especially in November. Okay, I don't know why they took that in here, but except saying that the planets appear near the ecliptic because they're nearer. They are near the same plane that the sun is at any time. So, interesting they put these two figures here. They seem like they fit better in the previous chapter. All right, so let's get on to 16.2, which is motions of the Earth. There are several motions of the Earth. We'll talk about them mostly on the next slide. But 3 of these motions are completely independent of the motions of Sun and the galaxy. So we're not going to worry with those to begin with. Let's just look at motions of the Earth that independent of the motions of Sun and galaxy. Well, number 1, every year we go around the sun. take a full circle around the sun, 365 in almost a quarter of a day. Okay? That's one of our major motions. But in addition to that, we're spinning. We're spinning every 24 hours approximately. We spin one revolution. Okay? So that's our daily rotation about our own axis. So this is once every 24 hours, once every 365 days. This one is incredibly slow. It's a clockwise wobble of our rotation axis. Right now it's at 23.5 degrees, okay? And but over time, and we're talking about multiple millennia, okay? We've moved ever so slightly. Sometimes it'll be less than 23.5, sometimes it might be a little more. But we wobble around our axis. Now that motion is called, and we're going to get to this a little bit later, precession. Now, I don't know if any kids today ever play with a top. Do you know of any that do? You have, okay. They're really sort of was fun to play with. You wrap a string around them, you do like this, and they get there and they spin. And they spin, the faster they're spinning, the more they're almost perfectly upright. But when they begin to slow down, you'll see them start doing this. Okay? That's precession. And that's what the Earth is doing, but incredibly slowly. So we'll get to that later. But that's completely independent of the sun or galaxy or anything else, our clockwise wobble of our rotation axis. Here are the other motions. Now this includes the ones we just said, but 7 conspicuous motions of the Earth. 7 conspicuous, but the last one is broken into 3 others, so it's actually 9. Those are less conspicuous. The first, like I said, our daily rotation, and we're spinning. It takes us 24 hours to spin once, but we're such a pretty good sized planet, that makes at the equator is spinning at, on the surface of the equator, is 1,670 kilometers per hour, okay? Now, that would be about 900 miles per hour. Someone standing on the equation is moving that fast around their axis. Of course, you don't feel like it because we're fixed on the Earth and you don't notice we're spinning, but we are spinning really quickly at the equator. Now, of course, on the North Pole, we're just, you're just twisting, okay? But you don't feel that either, okay? So that's our daily rotation. The monthly rotation about the Earth-Moon center of mass. Now, we're going to talk about this a little bit later. But I've already mentioned before you, get my globe out here. I've already mentioned that our moon is the largest relative to the size of its planet, Earth, of any. By far, there's no other moon that is anywhere close to the same dimensions of its planet as our moon is. And it's not close, but it's way closer than any others. Mars is the only other terrestrial planet with moons, and its 2 little moons, they are tiny compared to our moon. Really tiny. Jupiter, on the other side of the asteroid belt, and all the other gas giants, their moons, several of them, probably as many as 6 or 7, or maybe more, are larger than our moon. But relatively speaking, those planets, remember how big those planets are compared to Earth? And our moon's almost the same size as their largest moons. Our moon is larger than most of the moons, but almost the same size as the largest moon. So what does that mean? That means that when you might think that the moon just goes around the Earth, right? Wrong. When the moon's going around the Earth, the moon actually has enough gravitational field to make the Earth move around, not around the moon, but around the center of mass between the Earth and the moon, which would be somewhere about here. So that means we'll do this when the moon's doing that. So that's what they mean, the monthly, because the moon goes around us about once a month. You get the idea here? Moon month. You almost see the word moon in month, right? Just put an extra O there, you got it. The months are determined by the motion of the moon. The monthly rotation about the Earth-Moon center of mass. Not a big move, but it is. Happens every, goes through that once a month. The yearly rotation about the sun, in that we're traveling 106,000 kilometers per hour, which would be about 60,000 miles an hour. But again, we don't feel like we're doing that because we're on the Earth, and that's all we sense, that we're here. All right, now, the orbit of the solar system about the center of the Milky Way. Remember back in chapter 14, we talked about the Milky Way as a spiral galaxy, right? With a star cluster, a nuclear cluster, and just enormous number of stars in there. And then all these bands around there, pretty narrow bands, but long-reaching. And we're about 2/3 out one of those bands. So we're spinning around the cluster in the middle of the Milky Way at an incredibly fast speed, okay? That's at 370,000 kilometers per hour, which would be about 200,000 miles an hour. Whoa! We are moving, okay? That's our solar system's orbit about the center of the Milky Way, because we're out in one of those bands spinning around like a top. Number 5, the orbital motion within the sun's local star group, okay? So, not just us about the middle of the Milky Way, but we have a local star group that we're spinning within that group. Like, look at that. That's 1,000,000 kilometers an hour, which is about 600,000 miles an hour. Okay? That's moving. We also have the motion of the Milky Way galaxy relative to remote galaxies. And just the galaxy moving at about 580,000 kilometers per hour, which would be about 350,000 miles an hour, approximately. Goodness gracious, I'm getting dizzy moving so fast. Okay? Now, here's some minor motions. Okay? One of these is the changes in shape and size of the Earth's orbit. Now, we talked about this with Kepler's laws. Since we're in an elliptical orbit, not a circular orbit, there are sometimes we're closer to the sun and sometimes when we're further away. It's not a lot of difference, but a little bit. When we're closer to the sun, we tend to move faster. When we're further away from the sun, we tend to move more slowly. So those changes in the shape and size of the Earth's orbit, those are minor adjustments to these other things we talked about. Now, there's also, like I said, the slight change in the tilt of the Earth's axis. That's a precession. And that's incredibly slow, so we will never notice it in our lifetime. In fact, in the whole time that man has been on the planet observing things, our North Star has always been to the north. But sometime, hundreds of, tens or 100,000 years ago, it wasn't the North Star. It was at one time it actually was Vega, which is pretty far from it, but it's been in between that. So it's a very, very slow change in the tilt. And then here's the other one. We tend to be slowing down. I know I am. No, that's beside the point. Our rotation rate used to be just a little bit faster than it is now. So in maybe a few tens of thousands of years, our days may be 25 hours rather than 24. We're just slowing down ever so slightly. But again, in all the time that we've been measuring things, we haven't been able to detect much difference at all. Those are very, very slow changing motions. Okay? but they are real, as far as we understand. Now, continuing this, we have the overall picture now is we're moving, okay. Here's a picture of what we're talking about. I don't know if you know what a helix is. We're going around the sun, right? Okay? Earth is moving around the sun. But the sun's flying around the Milky Way and around, even more so, our local star group, the axis there. So the sun's going this way as we're going this way. So in reality, we're making this spiral motion like this, and that's called a helix. So we're moving along a helix at an incredibly rapid pace, going around the sun really fast, but the sun's going around the star group even faster, much, much faster. So we're spinning like this because we keep the sun in the center. Okay. Now, viewed from the Earth, the ecliptic plane is the plane of the Earth's orbit around the sun. Now, it makes it look like the sun follows that plane as it goes around the Earth, but of course we know it's really because of the spin of the Earth. We're going around the sun. Now the planets, the other planets, move in a narrow band about that ecliptic plane. So if we're going around the sun like this, the others are going maybe just slightly out of kilter, but mostly in the same plate. You can think of this as a plate, but it's a thick plate. Some of them going a little bit different from us. Okay? In other words, the solar system is relatively flat. Okay? Now, the sun is moving along an ecliptic across the background of the stars. Okay? Now again, we're changing our perspective here. Looking at the sun from where we are, we're seeing the stars that are over here right here. But then when we move here, we see stars that are here. When we move over here, we see stars that are here. So you see it looks like the sun moves along the ecliptic across different background stars. It really isn't. That's our motion that makes it look that way, but that's what it appears to be. And that's what I pointed out to you before, where the different planets or stars or other things are near that ecliptic plane at different months. They're not always at the same place, month after month. Okay. All right. I think we should have, nope. All right. Now, we're going to talk about not each, but a lot of these separately. Okay? We're going to start with our rotation, our spin of our axis. Okay? I think. Let me go back and look at this. No, we're starting with a revolution. So we're starting with yearly rotation about the sun. Number 3 is what we're going to talk about first. And we call this revolution. Okay? That's not taking up arms and overthrowing a government, as interesting as that sounds. No, we won't go there. This is talking about revolving around the sun. Okay? That's revolution. Now, in your text, this is called orbit. I don't know why they use different words here, but they did. Okay? Revolution on the slide set is similar to orbit in the text. This is the Earth's movement around the sun. Again, if Patel was the sun and I was walking around the outer bands of the classroom, that would be me revolving around the sun. Okay? The orbit defines the plane of the ecliptic. Where we are as we go around the sun, that defines the ecliptic. And of course, because we're tilted like this, at one time of year it'll appear one way and at other times another way. That's where you get the tropics, or it's where the sun is, okay, at different times of year. Okay? The ecliptic is the apparent path of the sun through the heavens as seen from the earth. Of course, the sun's pretty fixed. We're moving around. So what we're seeing, right here, I'd be seeing, I wouldn't see the stars, but if I could see them, I'd see the stars that are behind Patel. the ones I actually see are the stars over here, because it's only at night when Patel is set that I can see these stars here. Okay? But then a later time of the year, I'm seeing the stars over here. I can hardly see those anymore. Okay? At yet of that later time of the year, Patel's still the sun, I'm seeing these stars. None of those over there are visible. None. Okay? Now, we always see the North Star and the few that are around it. So those we'll see most of the time, if not all the time. But the rest of the stars, they're quite different depending on the time of the year. So the ecliptic is the apparent motion of the sun through the heavens as seen from Earth. It looks like the sun is moving as I move around, seeing stars, different stars. It's not. The sun is fixed relative to the stars. It's just we're moving around the sun, and that defines the ecliptic. Now that's ecliptic, as the sun is eclipsing different stars, just like the moon went through the shadow of the Earth. We saw a lunar eclipse last Sunday night. Don't confuse these words. We're in a elliptical orbit, not circular. So they sound alike, but they're a very different thing. Ecliptic is the apparent path of the sun around the Earth, which really is defined by our going around the sun. Our elliptical orbit is not circular. Now here, to me, was a surprising thing. We're actually closer to the sun in January than we are in July. And it's no trivial amount. It's 2.5 million kilometers closer in January and more distance, 2.5 million kilometers more distance in July. Now in miles, that would be about 1.5 million miles closer in January. 1.5. Of course, out of 93 million miles, what's 1.5 million? It's not a lot, but it is there. It's less than 0.1%. Okay, or right at 1%, sorry. Okay, now, let's think for a minute. I didn't say that right. Yeah, about 1%. Okay. Now, let's start with July 1st. July. Say in July we're here. We're actually further, further from Patel than I will be later. Okay? July we're here. Okay? Now, that doesn't matter. We're a little further. What matters is the sun's rays are hitting us more directly. So that's why we're much warmer in the summertime than we are in the winter. Because in the wintertime, even though we're slightly closer, okay, in January, slightly closer, we're tilted away. So the Earth's rays are oblique toward us, and they don't come in. That's why the sun rises later, doesn't climb as high, and sets sooner, okay? We have less sunlight, it's less direct sunlight, so therefore, the Earth receives about 6% more solar radiation energy in January than it does in July. So for us, thankfully, it moderates our extreme temperatures in winter and summer. We're a little closer in the winter, a little further in the summer. So guess what? It doesn't make a big difference. But think about the poor folks who are down in Australia, South America, Antarctica. They're further from the sun in their winter and closer in the summer. So that should make their extremes more extreme than ours would be, because they have not just the tilt, has them tilted toward the sun in January, we're also closer in January. And it has them not just tilted away from the sun in July, because theirs is opposite from us, they are also more distant in July. So they should have more extreme temperature variations. Now, I've never seen a definitive representation of that, so I don't know if you can really tell that much difference. My guess is you probably could. It might not be a lot, but it will be some. So, interestingly, you probably would have guessed otherwise, because it's colder in January than it is in July, but in reality, that moderates our temperature. It doesn't exacerbate the temperature changes. Okay, now, this is a gross exaggeration of what I was just talking about. This has June being way further and December being way closer. It's not that big, okay? It's just a little bit, about 1%. So you would hardly be able to tell it if they didn't exaggerate it, okay? But look at this. When we are farther from the sun, we're tilted toward the sun. So it makes up the difference that way. It's the amount of direct sunlight hitting us that makes the difference, not how far we are, okay? And in the wintertime, we're actually closer to the sun, so not as much sunlight is hitting us, but at least we're closer. That moderates that just a little bit. We're exactly equal in March and September, around the 21st, 22nd, something like that. That's why these are the equinoxes, exactly the same number of daylight and darkness hours on these days. Here, our nights are longer because we're tilted away from the sun, and our days are shorter. Over here, the days are longer and the nights are shorter because we're tilted toward the sun. Okay. Now, this then effectively defines our seasons. Okay? Our summer season, the day that we're tilted the most toward the sun, most directly toward the sun. Now notice here again how they have the sun way too small, the earth way too big. But that's just so they can get us all in the same picture. Okay? We're tilted toward the sun, and that's the first day of summer. Okay? And that's June 21st. And that lasts until the 21st, 22nd, 23rd, somewhere there in September, and that's when we're equinox. And that's the last day of summer, first day of autumn, the equinox. This is, again, the summer solstice, first day of summer, summer until equinox, which is the first day of autumn. That until December 21st or so, 22nd, 23rd, somewhere there, that's the winter solstice, when the sun quits dropping down and starts going back up. That's when winter begins, and it's that until spring or vernal equinox. That's the first day of spring, and that goes until the first day of summer again. Okay. So that defines our season. It's a combination of our tilt, mostly our tilt to the sun, and where the sun is. Maximum daylight, first day of summer. Equinox, first day of fall. Minimum daylight, that would be first day of winter. And equinox again, that's first day of spring. And it keeps running like that. Does that make sense? So you see the shape of our, mostly the tilt of the earth and our travel around the sun. That's what makes the seasons. All right. Now your book has at least one more figure here, and this is one we dealt with a lot in the last lab, so I'm not going to beat it to death, but it's showing a combination of the first and second lab. You see the Earth is tilted like this, right? There you see the Earth down here. This is celestial sphere over here. There's the North Star, so that would be the pole star, that would be directly over our North Pole, okay? The plane of the sun is like this. Our tilt is like this. So here's the celestial equator tilted just like we are. The sun being basically sort of, the ecliptic is fairly flat. When they intersect, those are your equinoxes. Spring equinox here, autumn equinox there. When they're maximum, the ecliptic of the sun is maximum height above the celestial equator, that's our summer equinox. And the sun kept rising every day until it slowed down, stopped, and started going down. that was the summer solstice, when the sun stood still, so to speak. Winter solstice is when it kept dropping, and then finally slowed down the drop, and then power started going back up. That was winter solstice, when the sun stood still in the wintertime. So we hit that in the labs. There's another illustration of it here. All right, that's your orbit or your revolution time. Now there is a little blurb here. And you should remember this one. What is the latitude of an observer who measures the sun's altitude of 38.5 degrees above the southern horizon at noon on the summer solstice? Okay? And they did some really weird math here. If the sun's altitude above the southern horizon, okay, that is the complement, in other words, 90 degrees off from what the latitude is. And they just did a really lousy job here with the math, so I don't think I'll even do any more. Okay. But I think they did it correctly. Okay. We won't go into that. We'd have to draw the pictures and all like that. So let's leave that alone. Now let's move to rotation. Okay, this is on page 412. Okay, bottom of the left-hand column. Rotation and the Earth's axis. The Earth's rotational axis is inclined at 23.5 degrees. We talked about that in the revolution. We're talking about it still. This, like we said, pointing out before, determines our seasons, determined by the orientation of the Earth's rotation axis relative to where we are in our trip around the sun. When we're most pointed toward the sun, that's our beginning of summer. When we're equinox, that's then fall. Pointed as much away from the sun as ever, first day of winter, and back on equinox, that's in the spring. Okay? So there's our thing. Winter solstice, summer solstice, that's the first day of winter and summer. Spring equinox, autumnal equinox, first day of spring and autumn. The celestial equator is tilted at that same 23.5 degrees with the ecliptic of the sun. So the line on the celestial sphere, that's what celestial equator is. We've talked about this before. If you imagine the Earth here at a certain tilt, then the celestial equator would be the projection of the Earth's equator on that celestial equator, the celestial sphere. So, nothing new there. Do I need this a little longer? No? Okay. Well, it's still up there. Okay. And this is the one I was just pointing out. I thought it was a page too soon in the book. This is the Earth at a tilt of 23.5 degrees. Okay? I think this is exaggerated a little bit, but maybe not. I don't know. And then directly over our North Pole would be the North Star. It looks like they don't have quite that in the right place, but close. There's nothing down here over the South Pole. It's just a big void of no stars. Okay. The ecliptic is the plane of the sun's motion. The celestial equator is the projection of the Earth's equator out in the celestial sphere. So, when the winter solstice is when the maximum deviation between the celestial equator of the Earth with the ecliptic of the sun, 23.5 degrees south of the celestial equator, that is your winter solstice, December 21st. Summer solstice would then be maximum 23.5 degree tilt above the celestial equator, and that would be your summer solstice. That's where the sun would be And that would be first day of summer, maximum day of sunlight. Okay, and then autumnal equinox is where the sun is crossing right over the celestial equator. At that point, that would be autumnal equinox. When it happens in the spring, that would be the vernal or spring equinox. Okay. Kind of makes sense. Then saying and hitting it and doing it over and over again. So it should be pretty much in understood, hopefully, by now. All right. Now, we were just talking about rotation of the Earth, and then we asked the question, it seems like a dumb question now, does the Earth rotate? Okay. Now, in the old days, they would have said, no, we're fixed in space. The sun moves around us. But we know that's not true anymore. The sun's fixed, we spin, it makes it appear that the sun is rising and setting. It's still, we're just spinning. But, is there any other evidence? And these were some things that Galileo, for instance, studied. With our telescopes, Galileo improved on the telescope enough he could see this. You can see that other celestial bodies do rotate. Now, you'll never see a star rotate. That's way too far away. Can't possibly see that. But don't ever look at the sun, see if it's rotating. You'll kill your eyes that way. But people have taken pictures of the sun or looked at it indirectly, and you'll see that it indeed is rotating. And Jupiter is the other main character we can tell it's rotating too. That great red spot, that's our friend there. We see it moving around. And with stronger and stronger telescopes, you see other features moving. So we know those objects rotate. Well, if the sun's rotating, Jupiter's rotating, we think the others are all rotating, why wouldn't we be rotating? Of course we would be. Okay. That's one bit. Here's another piece of evidence. Any of you, have you ever seen what they call a Foucault pendulum? I don't know if that's how you pronounce it. Foucault, I don't know how you pronounce it. I believe it's Foucault pendulum. They have one, or had one at the McWane Science Center. I don't know if it's still there, but I don't know. I hope it's still there. What it is way up at the high ceiling, they have the thing, and the pendulum is going back and forth, and you see approximately where it is relative to a circular grid on the floor. And at different times of day, you'll see the pendulum is doing this, okay? It's constantly changing. You can't tell it looking one time to the next, but if you wait a few hours and go back, you say, yeah, that's moved. Well, the reason it's moved is the Earth is spinning. It's trying to maintain the same thing, but with Earth spinning, it seems to be moving. The pendulum oscillates in a fixed direction. The orientation changes as the Earth rotates. Now, they give this example, and I've never actually done it, but I think you can imagine it, okay? If you had a stool that you could spin, maybe those in the labs you might be able to spin, I don't know, and you set up a ball going back and forth like this from, this is a very good illustration. This makes it look like there are two balls there. You got one ball that's doing like this. But then when you spin this, the ball's doing like this over here, like this over there, like this over there. So it's changing direction all the time. That's why the Foucault pendulum is changing direction, because the Earth is spinning. The orientation changes as the Earth rotates. So that's another piece of evidence. And you can see that and observe it in reality. Okay? There's another one. The Coriolis effect. Okay? If you were to be way up in a jet airplane, perhaps a very high-flying balloon or something like that, and you were to drop something toward the Earth, you would notice that from the Earth, very slightly, it appears that it has a bend in the path. That's called the Coriolis effect. Now, there's a potential paper topic, isn't there? Here's one here. Foucault. Who in the world is Foucault? How did he develop his pendulum? How did he illustrate it and do it? He was from France. He did it in Paris, I believe. That's a potential paper topic. Here's another one. Coriolis. Who was he? I'm pretty sure he was Italian. That sounds like an Italian name. How did he determine this? How did he come up with it? You know, several different potential paper topics there. But this is that apparent motion of a deviation or deflection in path as something false. Now, whether you realize it or not, you've all witnessed this. Okay? Have you ever pulled the plug on a sink full of water? What do you notice happening? The water just... Does it? No! It also spins. It twirls. Now, did you grow up in the U.S. or in India? India. How far south?
West.
West, okay. So you probably are about the same as you are here in the U.S. People who lived on the equator, like that one student that I had who was from Kenya, more than likely, there when you pull the plug, the water just goes down like that. But when you're either in the northern hemisphere or the southern hemisphere, the further you are north or south, the more you'll see that spinning motion. Okay? And that's because the earth is spinning as the water's falling, and as it does, it makes it look like it's spinning too. Okay? Now, another illustration of how weird physicists are. Okay? I had a professor at Georgia Tech when I was an undergraduate. I had him for one course as a grad student as well. But in one of the undergraduate courses, I think I had him either 1-in-1 or 2-in-1, something like that. But in the undergraduate course, one of the undergraduate courses, he told the story on himself. He was, I didn't know at the time, but I found out later, he is was a honcho in crystallography. I mean, he was one of the world's best-known crystallographers, physicists, studying that. And he was actually, if I'm not mistaken, the main editor of the major crystallography, International Crystallography Journal. He was a honcho, okay. And as a honcho, they had the International Crystallography meetings one time down in Rio de Janeiro, Brazil. Now, if anyone knows much about Brazil, you know the two major cities, Sao Paulo is over here, and Rio is over here. Rio is right on the coast. Sao Paulo is just a little ways inland, but they're really close to each other. Now, neither one of those are the capital. Brasilia is the capital. It's way in here, but it's really minor compared. It's sort of like New York and Los Angeles, really major cities. Washington, D.C. is a major city, but not nearly as big as either one of those. Well, same thing here. Well, Sao Paulo is the business capital, the working capital of Brazil. Rio, party city, okay? Beautiful city, from what I understand. I've never been there, but it's the playground, okay? Right on the coast, beautiful beaches, warm temperatures. It's just above the Tropic of Capricorn, so it's pretty nice weather down there. It's a party city, okay? So here, Dr. Young had his international crystallography meetings, honcho in the crystallography, down in Rio de Janeiro. Most of the time it was always in Europe, America, somewhere else, always in the northern hemisphere. His first time ever to be in the southern hemisphere. Okay? Now, the Coriolis effect, because it depends on where you are on the globe, on the equator, water just tends to go straight down. But north or south, it gets that spinning. But northern hemisphere, it spins counterclockwise, southern hemisphere, it spins clockwise. So Dr. Young arrives in Rio de Janeiro, party city of the southern hemisphere. All the southern hemisphere. I mean, it's that, okay? And he gets there, and he said, I couldn't wait to get to my hotel room, run into the bathroom, and flush the toilet, just so he could see the water spin in the opposite direction. Goodness gracious, what excites a physicist, you know? Water going down the toilet, okay, in the party city of the southern hemisphere. That's the Coriolis effect. Deflected paths of the Earth of motion as anything is moving because of the Earth's rotation. Okay. All three of those are reasons that we have evidence that the Earth is really rotating. It's not just made up, it really is rotating. Okay. Now, the next, and this is the last of those three, remember way back, here I sort of said it wrong. Remember, here we said the three main motions of the Earth, revolution first, rotation second. Now we're doing precession. So, it took us a while to get here, but here they are. There we are, precession. This is, and when it says slow wobble, they mean really, really slow wobble of the Earth's rotation axis. This is a reaction of the Earth to gravitational pull on the equatorial bulge. Remember, we bulge out in the equator some by both the moon and the sun, and this makes this wobble just a little bit. Very minor, but it's up. 26,000 years for it to go through one precession. One rotation of this. So just because the North Star is our pole star right now, and it will be throughout our lifetimes, especially mine, it will deviate in about 13,000 years. It'll be something else, like Vega or something like that. Well, give it another 13,000 years, and we'll be back with the North Star being our pole star again. So the changes direction of rotation axis on the celestial sphere, Polaris has not always been the North Star, nor will it always be the North Star. It is right now, but it won't always be. The position of the equinoxes in the zodiac changes. Now what that means, the equinoxes, yeah, that's going to affect those a little bit, but basically what it's meaning is, another meaning here is, do any of you follow horoscopes and things like that? If you might, I don't, but you have all these constellations that represent where the sun is along its ecliptic. And there's 12 of them, Leo and Sagittarius and Pisces and Virgo and all these, there's 12 of them around there. But guess what? Some of those aren't quite on the ecliptic anymore because we're wobbling just ever so slightly. Some of them, there's something else that's closer now, but we leave those as they are because that's what they always have been, and nobody likes to change. Okay? I think Mr. Weigel at the planetarium may go into this some in the future when we go to make our visit there. So I think that's what they're meaning about. Position of the equinoxes in the zodiac changes. That seems like the wrong word. It seems like position of the eclipses. I think that's what they meant in the zodiac changes. But I'm not sure. Just a weird way to phrase it, I think. Everybody got that? I'm trying to wait for all of you to finish. Oh, and here's the top example. Now this is a gross exaggeration, but it is. When a top is spinning really fast, it usually doesn't move much. Sometimes you'll see it wobble really quickly like this, but when it slows down, you'll see that it does begin to do this more and more. So that is what we mean by precession of the axis. Again, this is grossly exaggerated here, but let's, rather than the top, put the Earth in there. Here we go. Okay, right now we're tilted at 23.5 degrees, and the North Star is just about over our axis. Doesn't wobble, it doesn't move much, but in about 13,000 years, we will have wobbled a little bit until we're over here in Vega. That'll be about 14,000. We got a long way to go. A long way to go before we're going to lose the North Star as a pole star and pick up Vega. There may be some other stars that will fit better for a while, long while in between, but we're not going to be around to see it. It's going to be North Star as long as any of us are alive. Sometime in the future, it'll become some other star that might be out here somewhere. About 12,000 years from now, it'll be Vega. Okay. And about 12,000 years ago, it probably was Vega. Vega is a much brighter star than our North Star. All right. Any questions on that?
So does that affect the seasons?
It probably will. They'll probably still be basically when they are, but it may affect how extreme they are. You know, it may make it, if it gets less than the 23.5 degrees, then equatorial things will get hotter and further north will get colder because of not as much. So in that sense it will affect, but it probably won't affect the timing of them. We'll still have the 4 seasons, I think, about like they are. But I won't be around to care. You know, it's going to be that long in the future. All right. Now we're moving toward place and time. This is 16.3. Okay? Now, we've already been hitting on this a lot. In fact, a lot of the last lab we were doing some of the same stuff. Okay? So, Earth's periodic motions, both as we go around the sun and as we spin on our axis, they provide a basis for determining place and time. Now, it may not be as obvious to you the place part, but it really is. Time, certainly. Okay? The rotation provides an axis of rotation useful in determining locations on the globe. What locations? The obvious ones are the North Pole and the South Pole, right? That's where the axis of the Earth is. Everything spins around that. Did I spin it the right way? I think so. Yeah. Okay? Now, but just like you can fix the poles exactly where they are, equidistant from the poles is the equator. So you can fix that exactly where it is. Okay? So the rotation provides an axis of rotation useful in determining locations on the globe, specifically the poles and the equator. And then everything in between as well. But those are the main things. Now, a combination of the rotation and the revolution determines the cycles which can be used for time standards. For instance, seasons. Okay, well, number one. Rotation determines day length. Revolution determines year length. And then the things we've already mentioned about the ecliptic, angles and stuff like that, that gives us the seasons. So in addition to days, years, seasons. Okay? So a combination of rotation and revolution determine those cycles which can be used for time standards. And are. Okay. Leave that for a little bit. Now, the place thing, yeah. The poles, the equator, and then increments around the equator, or between the equator and the pole. That's certainly important stuff there. Time, days, years, and seasons. Those are the main ones. Every other thing is involved too, but increments between. Okay? Everybody got it now? Another one more, still right. here is partially the problem, but also suggests sort of solution. Let's talk about place. Now, at one time, not too many hundred years ago, most people thought we lived on a flat planet. Because as far as we can tell, everything's pretty flat, right? So I think there's still a facetious organization called the Flat Earth Society, okay? I don't know what they do, but I've seen that name before. If we were on a flat plane, all you would need to know is the intersection of two straight lines, okay? Think of our Cartesian coordinate system right here. This is also a math classroom. You have a horizontal axis there, a vertical axis there. So anything that's in a plane, you can pick a point and say, how many units from the y-axis, that's your x-coordinate. How many units from the x-axis, that's your y-coordinate. There you are. You can fix it from those two measurements. Perfectly fine. Intersection of two straight lines. Since we live on a spheroid, that doesn't work. You don't have any straight lines there. Everything's curved. Everything is curved. So we got to have a different way for identifying where you are on a curve. And here's what we use. So there's the flat page. So pick a reference. Say the center part of the book. Open your book, take it along the center line, and say we're going to go from exactly equal distance from top and bottom at the center of the book, and then any place on either page you can measure how far from it is this way and how far it is from the top of the page and wherever. The distance from the left side of the page, distance from the top of the page. All you have to do is pick out what you're going to do. They really said this back. Okay, yeah, left side of the page. I guess that's okay. You can figure out exactly where you are. Curved surfaces, not. Okay? So here's what we do on a curved surface. Like I said, the two fixed points, North Pole, South Pole, and then the line around the center, the equator, equal distance from the. Let's call that equator 0 degrees. So let's imagine you got a protractor. Do you remember those from way back in school? And you sat right in the center of the earth, and it didn't melt or anything. And then you measure, that's 0 degrees, and then you measure up from the center 20 degrees, 40 degrees, 60 degrees, 80 degrees, 90 degrees. Most of the time we do 15 degrees, 30 degrees, 45 degrees, 60 degrees, 75 degrees, and 90 degrees. Something like that, okay? That's how we measure north and south of the equator. We split it into circles. Now these are called parallels because each circle is parallel to the previous one. They're getting smaller because the Earth is getting smaller the further you go up. But these are your parallels. Also called latitude lines. 20 degrees north, 40 degrees north, 60 degrees north, 20 degrees south, 20, whatever. Those are your parallels, also called your latitude lines. Okay? And this is how you picture it again. Say you took a slice in the middle of the earth, put a protractor in there. This would be 0 degrees, 20 degrees, 40 degrees, 60 degrees, up to 90 degrees. Okay? That's how you would visualize it. And those on the surface would determine your latitude lines. All right. However, for longitude, latitude, you're going to measure from the equator. That's 0. That's right in the center, okay? North or south, up to 90 degrees north, 90 degrees south, okay? Longitude is a little bit harder. Number one, where do you start, okay? We'll determine that. We start at what we call the prime meridian. Remember, a meridian is from due north to due south, directly overhead of wherever you are. So we'll start with this one, and we'll call that 0 degrees, the prime meridian. Now, how they selected this, when they selected it, England was queen of the ocean. England was the most powerful empire in the world. Remember when they used to say, the sun never sets on the Union Jack. Britain, Great Britain, ruled the roost. And because she did, and her biggest strength was in her navy, not necessarily her army or navy. She was queen of the oceans, remember? Island country, she could get anywhere from where she was easily, relatively easily, more easily than many other countries. Okay? Now, so they chose the place where the British or English Naval Observatory was. That happened to be just a little bit east of London in a town called Greenwich, England. So that's why we have prime meridian is also called, when you're measuring time from that, you say Greenwich Mean Time. That's the line that goes through Greenwich. And there it is. Here's the 0 degree longitude now, and this is right through Greenwich, England. There's London, just a little bit east of London is Greenwich. Now, just a little side story. My wife had professional meetings that were coming up in Paris. This was several years ago. And she just decided to ask her oldest niece if she wanted to go with her. I think it was going to be a time that Julie could do that. And so Julie said, yeah, I'd love to go to Paris. So Karen started figuring for her to travel with her to Paris. And when Karen was in a meeting, she could hang around the room and enjoy whatever. But then when they weren't in the meetings, they could go out, tour around. They get there early and leave later, see some of Paris. Well, Karen's mom heard about that. And she said, I want to go. Okay. So now Karen's mom and her niece were going. Well, then Karen's sister heard that from her mom. So well, I want to go, you know. And so does Michelle. That's the younger niece. So, okay. So all of and Julie, the older niece, was Karen's brother's daughter. So Karen wound up having a group of 5 that she was going to be hauling around. She said, I'm not going to have time for my meetings. So she just gave up on the meeting. She was going to have to pay for it anyway, parts of it. So she gave up on going to the meetings. And then the trip expanded to be, I think they flew into England, traveled over to Paris, flew into London, traveled to Paris, and then flew back from Paris. So that was going to be the trip. And there were some other different, but anyway, that was it. So they started off in England. And one day they took a tour to the Naval Observatory outside London. Not far to go at all. And they went. And the crowds were just enormous. And Karen said, what's the big deal about the Naval Observatory? Sure, it's the prime meridian, that kind of stuff. Why are all these people here? Well, she found out then the Queen was coming to christen the newest building on the Naval Observatory campus or something like that. So it was a big deal. So Karen and her sister and her 2 nieces and her mom got to stand along the parade route and see the Queen wave at them. Okay, as she waved to everybody. Okay, so she got to see the Queen in Greenwich, England, because of that. So anyway, that's the prime meridian. Goes through the Greenwich Naval Observatory in Greenwich, England. That's the 0 degree longitude. Now this time we're going to take our protractor and lay it flat. And from that meridian going east, you go from east, let's do again, 15 degrees, 30 degrees, 45 degrees, 60, whatever it's going to be, up to 90, 120 to 180 degrees east, or you can do the same thing to the west. So whereas latitude goes from 0 to 90 north, 0 to 90 south, longitude goes from 0 to 180 east, and 0 to 180 west. Okay? Because you're going this way. These longitude lines don't get any smaller. These are all what you call great circles. And they do. They get closer together toward the poles, further apart around the equator. But those are your longitude lines. Now the parallels, the latitude lines, the only one that's a great circle is the equator. That is a great circle. The others are getting smaller as you go north or south. But those aren't parallel. Those are called the ones, latitude or parallels. These aren't parallel because they all intersect on the Earth's axis. Okay, so that's your longitude line. With those two, you can locate any place on the globe. Now, not this coming lab, but a future lab, maybe the next one or two from now, we'll actually be doing latitude and longitude. You see, we don't have labs to do everything, but everything we do in the course will be related to the labs. It may not just be at the right time. Okay. Now, position on the Earth is determined by the intersection of your parallels, or your latitude lines, with the meridians, which are your longitude lines. And this defines any location. Just like XY determines it on a plane, latitude, longitude determines it on a globe. So let's see where we are. This is approximate. We've already given the latitude of where we are, 33 degrees, 23 minutes, 45 seconds. That's very precise. Longitude, we're fairly close to 90 degrees west. That goes through New Orleans and Jackson, Mississippi. 75 degrees west is 15 degrees further. Boy, that's way up there in Dover, Delaware. So way up there. So we're closer to 90 degrees west, Jackson, Mississippi. There's Alabama, there's Birmingham. To me it looks like we're maybe about 86 or something like that degrees west of the prime meridian. Here's the prime meridian right here, almost a quarter way around the globe from that, about 86 degrees west. We'll get exact measurements later. So the parallels measure latitude, the meridians measure longitude. Okay? And with those two, you can pinpoint any surface on the globe. Any surface. Okay. And again, here's a picture of the parallels or the latitude lines, the cutaway view of how they get them, the picture of the longitude lines, and the cutaway view of how they get them. Now, there's nothing too new here. Everybody got this so far? Okay. There are some special parallels that are climate related. And again, we've already mentioned these, but we'll bring them up again here. Okay? Let's start with primary parallel. That's the equator, 0 degrees, north or south. Okay. Now, because we're tilted 23.5 degrees, the Earth's axis is from the plane of the sun, 23.5 degrees, there is one time of the year when the sun is directly overhead this latitude line of 23.5 degrees north. Okay? And when it is, that's directly overhead. Never does it get directly overhead anywhere north of that. South of here, it'll be twice a year, once before this, one after this, all the way down until you get here, once a year at 23.5 degrees south, right there, directly overhead. And this one at the bottom is called the Tropic of Capricorn. I just mentioned that when I was pointing out Rio de Janeiro. And then the Tropic of Cancer is the north. Tropic of Cancer just below the tip of Florida and above the northernmost part of Cuba. You know, Cuba and Florida are not that far apart. What is it? 60 miles, 180 miles, something like that. Tropic of Cancer goes right in between those two land masses. Okay? So those are two more pretty important parallels, where the sun's directly overhead on summer solstice where it's directly overhead on winter solstice. Tropic of Cancer, Tropic of Capricorn. 23.5 degrees north of the equator, 23.5 degrees south of the equator. Okay. Now, those aren't the only two. Here's two more. The Arctic Circle is that 23.5 degrees is still involved here. 23.5 degrees south of 90 up here, and 23.5 degrees north of your 90 degrees down here for your South Pole. Now, what's special about that? That is the circle there, 23.5 degrees south of the North Pole, north of the South Pole. That is the place where, right on the Arctic Circle, is the first place that you have 24 hours of darkness in the winter and 24 hours of daylight in the summer. Everywhere above that, you have several days, okay? But on the Arctic Circle or Antarctic Circle, you have that one day that would be 24 hours of darkness, 24. And another day in the winter, 24 hours of daylight. Not a back. 24 hours of darkness in the winter and 24 hours of daylight in the summer. Okay. So those are all, and whereas these are 23.5 degrees north and south of the equator, these are 23.5 degrees south and north of the poles. So if you subtract 23.5 from 90, you'll get 66.5 degrees. So that's where your Arctic Circle is. Okay. Above that, frigid. Below the Antarctic Circle, frigid. Okay. In between the tropics, very, very warm. In between the tropics and the Arctic and Antarctic Circle, you'll find what we call the temperate region. That's where we live. It's sort of in between. Not super hot, not super cold. So those are climate related. All right. How are we doing on time? Okay, we still got a ways for our 2-hour mark. Let's see how we're going to do. We might actually make it. If we don't, we're going to be awfully close. Well, we still got the moon to do. Nah, we probably won't make it. Well, let's give it our best shot. Okay, measuring time. This is the next part of place and time. We talked about place, now time. The time standards depend on measuring intervals between evenly spaced periodic events. Okay? Yeah, we've already done some of that. The last lab we did. Astronomical examples. The rotation of the Earth on its axis, that defines a day. Revolution of the Earth around the Sun, that defines a year. So the rotation, basis for day. Now, what's the basis for our months? I mentioned it just briefly earlier, and we haven't gotten to it in the text yet, but since they mention them here, what is the basis for the month? What word do you almost see in the word month? Leave off the moon. The moon, that's the astronomical basis for our months, because we have approximately 12 cycles of the moon every year. It's not exact, but it's close. Okay, seasons, we've already seen that. That has to do with the tilt of the Earth and where we're facing at any given time. Okay? Between our equinoxes and our solstices, those determine our seasons. And year, of course, is one revolution around the sun. Okay. Now, in the last lab, we already looked at different ways to measure days. We didn't look at different ways to measure months and years, but they're fairly similar. Okay, so that's going to be part of what we're going to be doing now. People still writing? No. Let's see. Finish up. Okay. I'll refresh your memory on the days. We have two types of days. We have the solar day. That's the time period between the crossing of the sun over our local meridian from one day to the next, that's one solar day. That's a little bit different from the days based on stars. Based on stars, that's called a sidereal day. Sidereal meaning stars, I guess. Okay? Now, why is the difference? Because you see, for the sun to cross our meridian, we're spinning once, but we're also moving around the sun, so it takes about 4 minutes longer for us to spin till the sun crosses meridian again, because we've moved that far around the sun. Okay? About 4 minutes more. So a solar day is about 4 minutes longer than a sidereal day, approximately. Okay? We'll see the same things. In sidereal day is reference to a star. Stars are always fixed there, so it's one revolution that's going to make us a sidereal day. But it's a revolution plus a little bit, about 4 minutes more, will make a solar day. Because we go from noon to noon. So everybody finished that so far? Are you still writing? You got it?
Yeah.
Okay. So let's look at daily time. That's as opposed to time daily. No. Okay. Daily time is based on the Earth-Sun motion. If you viewed from the North Pole, the Earth revolves, should be rotates. Oh, no. Viewed from the Earth, from the North Pole, the Earth is going counterclockwise around the Sun. Get that right? Yeah, I was going right. Counterclockwise around the Sun like this. Revolves. I thought they were meaning rotating, but it's revolving. It rotates in the same direction. So we're going around the Sun in this direction, but we're also rotating in this direction. Okay? Everything going counterclockwise. Why didn't we have our clocks going counterclockwise? Then everything would be clockwise, wouldn't it? Never mind. Okay. Now, on Earth, because of that, it makes it seem like the sun rises in the east and sets in the west, because the sun is fixed, and as the Earth spins, you see it first in the east, noon, and then setting in the west. Okay. So that's what it looks like here on Earth. Still right. Oh, I think when I hit this one, that writing will stay up there. Yes. So here's the difference between a solar day and a sidereal day. Now this is greatly exaggerated. But let's say that the Earth is right here, and right at this point here, one rotation of the Earth from this point here, the sun is directly overhead. That's noon that day. You revolve around the sun a little ways. Now this is greatly exaggerated, but a little ways. Well, one rotation later puts you right here. But that's not with the sun directly overhead. You got to spin for about 4 more minutes to have the sun at noon again. Okay? So that's why a solar day is about 4 minutes longer than a sidereal day. If you're looking at a star over here, you're right there is that star at, say, midnight, and then one day later, the star is still right there at midnight. So that would be a sidereal day about 4 minutes shorter than the solar day. Okay? Does that kind of make sense? Because we've gone a little bit of ways around the sun. Now remember Venus? Venus goes around the sun too, same direction counterclockwise, but much, much slower. Okay? If my memory's right. But not only that, it spins backwards. Venus spins backwards. And its days are longer than its year. So I may be wrong. It may go around the sun fairly quickly, but it rotates incredibly slowly. Okay. Then way out there, Uranus, I think it is, spins like this. It's not clockwise or counterclockwise. It's that it's tilted it totally wrong. Okay. So, anyway, we're talking about Earth now. So don't forget about them. Those are on the test, but we're talking about Earth now. Everybody got it? So let's talk about the sun's motion across the sky. And we've already said this several times, so I'll try to go through it quickly. Noon. Noon is when the sun reaches the maximum peak, and that's actually right when it crosses our celestial meridian, our local meridian. When it crosses that, that's as high as it'll ever be. That's our apparent local noon. Now, when I was in the Navy, we called that local apparent noon, LAN. The book now, or people call it apparent local noon. The time at which the sun is at our celestial meridian, which is the highest point it will ever be in that day. Apparent local noon is at a particular longitude. So this would change if you went east or west, your local noon would change. So we don't have it do that. We'll talk about how we fix that later. Okay? Now, the apparent local solar time would then be given by that position of the sun in the sky when it crosses our meridian from one day to the next day. And that's measured with a sundial. Now remember, there are two words for sundial. Three words. Sundial is one. That's the one that gives you the time based on the shadow from the sun. The other name for that one is called a gnomon. Never use that, but a gnomon. Sounds like the word for gnome, which are those ugly little figures they put in the garden. I don't know if those are related or not. Okay? But that would be close to your local apparent solar time. It's not the time shown on clocks because depending on where you are, it may be off a few minutes one way or another. So what we do, we take those solar times, average them over an entire year or whatever, and that time average on apparent solar time, that would be what we call a day. Averaged over two effects. First is the Earth's orbital speed changes as it goes through its elliptical orbit. When it's furthest from the sun, it's slowest. When it's closest to the sun, it's moving fastest. So it averages those, and it also averages the incline that we have. Averages that. And we did this in the last lab. What was the other name for a sundial? Not the one that gives you a shadow. It's the one that forms that figure 8. That word is analemma. I started to say something with E. I said, that's not right. Analemma. A-N-A-L-E-M-M-A. We'll get to that a little bit later. Okay? It's different from the sundial that we call the gnomon. This is the figure 8 that you get. And we could get it if we, like I said, put a hole, covered the windows and just let light come through a little hole, and at noon, apparent noon every day, we marked where that was on the floor. We would draw our own gnomon over the year. And that's why sometimes you're ahead of local noon, sometimes you're behind local noon. We did that in the last lab. Okay. So the mean solar day, when you average all those things together, it's 24 hours. Okay? That is the length. Some days, noon to noon will be longer, and some days noon to noon will be shorter, depending on how fast or slow we're moving around the sun. And a little bit on our tilt. I'm really noticing now that I didn't finish lunch. My stomach going, oh, okay. I'll finish after y'all finish your test today. And then I'll go home and eat supper. Everybody got it? Okay. So what is a day? A day is a day is a day. Okay? It's the length of time required for the Earth to rotate once on its axis? No, that's a sidereal day. Okay? The interval between two consecutive crossings of a celestial meridian of any particular star. Not the North Star, it's right on our meridian all the time. But any other star from it time crosses one time to the next, that would be one spin of our axis, that's a sidereal day. Reference to the stars. Little variation because the Earth's constant rotational rate, doesn't matter where we are around the sun, the stars, or where they are, they're always going to be there. Okay. But the solar day, the apparent solar day, is the interval between two consecutive crossings of the celestial meridian by the sun. So here we have two things in effect. One is the spin of the Earth, but also you have to take into account our revolution about the sun that changes the Earth-Sun orientation every day. About 4 minutes longer than the sidereal day. Now they have this backwards. This should be over here. The sidereal day is about 23 hours, 56 minutes, and 4 seconds. The solar day is the 24 hours. Okay? They don't have that on here, but this should be over here. That's the length of a sidereal day. The solar day is right at 24 hours. 4 hours added to that would be 24 hours and 4 seconds. So that's where the about comes in. Okay? Sidereal day, about 4 minutes shorter. And that's because that's the time it takes the Earth to move one day around the sun. It adds about 4 minutes to noon to noon. This making sense? Okay. Goodness, I'm so hungry. I need to keep talking so I don't think about how hungry I am. Doing your writing, I would put this over here, under here. They just put it there to even up the top, but it really belongs over here. Now remember, the solar day, though, is averaged because when we're moving faster, crossing the crossing day won't be quite, it'll, won't be quite 24 hours, but when we're moving more slowly, it will be a little over 24 hours. So they average it over the entire year. That's where we come up with the 24 hours. The sidereal day is not affected by that because who cares how fast we're going or how far we're going around the sun? Immaterial, the stars are out there no matter where we are at basically a fixed distance. Okay, everybody got it? Over there? I hope so. Got it? Okay. All right. Now, we talked about the second name for a sundial being the analemma. And another way to refer to that is the equation of time. This traces the yearly variations between apparent local time and mean solar time. Okay, this is that figure 8 that you could do on the floor. Like I said, if we block the windows with black plastic, cut a little bitty hole at a judicious location in the black plastic there, and then at exactly our local apparent noon, when the sun crosses our meridian, we're able to mark a place on the floor every time where the sun shone through that hole, you would get a figure 8 over a full year. Two effects: the axis tilt, the north-south motion, and the orbital speed, and that's when sometimes we're going faster around the sun, sometimes we're going slower. That all affects. The axis tilt is our north-south motion, and the orbital speed would be the east-west motion. Okay. The equation of time is a cumulative plot. Now the ones they show here, and you can get these words because it'll stay up for a bit. This isn't quite the figure 8 that we're talking about. This basically is the path of the sun. This is at vernal equinox, at summer solstice, at autumnal equinox, and at winter solstice. This is just describing the ecliptic. You know, if you wrap the earth around, that would be the slice that the sun's path would be. That's not the figure 8 we're talking about here. That contributes to it. That contributes to the north-south features of the figure 8. Right here, we're going to be right on that equator. Here we'll be at the northern part. Here it'll be at the southern part. Okay, but that doesn't make the figure 8. That gives you the position north and south of the equator. Okay. Now, this is closer to that figure. Okay. This is the clock time behind or ahead of the shown by a sundial. So that's where the analemma, meaning sundial, comes into play. Now if you were to take this figure, fold it right there, fold this over here, then you see this and this make the little part of the figure 8, and these two make the fat part of the figure 8. That then would be our analemma, or the that would give you that same thing. But what they did this in a linear type sense rather than the position of the shadow, or actually the sun shining. And remember, half the time we were ahead, but it crossed, you know, and each of these are the day of the year. So around the late March, early April, you're right on the money. I was thinking that was closer to April the 15th. Here you're right on it again. Here you're right on it again in August, but this is where they crossed and made the figure 8, and then came back here and you're right on it again. Okay. Kind of makes sense. Your lab, and once y'all turn that in, trying to get those graded when I get them back to you, you can have that if you want it for future reference. Okay. We have a problem though, don't we, Houston? Whatever day of the year this is, there we're just about the sun directly overhead. This will be noon on that day, right? Guess what? It's not noon on that day here. It's afternoon. Here it's well afternoon. Here it's morning, because the sun's not directly overhead except right where we are. Okay? Over in Atlanta, that would be 11 o'clock. No, 1 o'clock. Over in California, that would be 10 o'clock. What's going on here? Well, noon is where the sun is relative to you, but on a different part of the globe, the sun's not going to be that same thing at that same time. So what we do to account for this is take our 24 hours in a day and 360 degrees around the globe and divide 360 by 24. So someone do that. 360 divided by 24. I think we've done it several times already. Someone who has a calculator. 360. Say again?
15.
15. That means every 15 degrees you could be in the same time zone. So let's take where we are. We're close to 90 degrees north. And let's do 15, which is 7.5 degrees here, 7.5 degrees there. Yep, Birmingham's in that. Atlanta's just on the other side of that. So that's why they're on a different time zone, even though we're so close together. But most of Texas is still on our time zone, where we're much closer to Atlanta than we are to Texas. It's just where the time zones fall. Okay? So sure enough, we are in that, we call that the central time zone. Each one of those is about 15 degrees longitude, approximately 15 degrees longitude. Now, these are adjusted for local consistency. What do we mean by that? Well, are any of you from anywhere close to Phoenix City? Any of you ever been to Phoenix City? Not Phoenix, Arizona, Phoenix City. Okay. Are they on the same time zone as we are? They are. Okay. Well, at least most of them are. The writing is still there. Here's what we mean adjusted for local consistency. Phoenix City, Alabama is real close to Columbus, Georgia. Phoenix City is sort of a small town. Columbus is a pretty good-sized city, okay? And Columbus also has Fort Benning and a lot of other employment there. So a lot of people in Phoenix City will just set their clocks by Eastern time zone rather than Central time zone, okay? Just because they work there, they shop there, they live there. I mean, they live over here, but they're close enough there. Well, that happens all over the country. For instance, up here in Maine, Maine should be, or at least half of Maine, probably more than half, should be in what they call the Atlantic time zone. But we put them in Eastern time zone so they can be with the rest of the country. See, every other state over here is in Eastern time zone. They would be the only one there. So they adjust this for local consistency. Right here, does anyone know what happens right in here? If this is Illinois, what city is right there? Chicago. Chicago, Illinois is on the Great Lakes there. I think that's Lake Superior. It's Lake Superior. Chicago is on there. So a lot of this area around here wants to stay on the same time Chicago's on. So they do that. They adjust this, wiggle it around so they're on the same time zone. Now, poor old Upper Peninsula of Michigan. This is all the state of Michigan, but because the people from UP, Michigan, mostly are going to come down here, they get on, I'm sorry, I said it wrong. Here's Wisconsin. And part of Wisconsin and UP Peninsula, it's up there. So they split it right down there. Sort of bizarre. This is Central Time Zone, and it's east of Eastern Time Zone here. So they adjust it for local consistency. Poor old Tennessee is such a long state, and Florida too. Pensacola, Florida is on Central Time Zone, whereas Tampa and Tallahassee and all these others, Orlando, are on Eastern Time Zone. I'm saying everything backwards. Tennessee, Nashville and Memphis are on Central Time Zone, but Knoxville and Chattanooga are on Eastern Time Zone. Kentucky, Eastern Kentucky is Eastern Time Zone, Western Kentucky is Central Time Zone. The tip of Indiana, because down here you're closer to the areas of Illinois here that they do their shopping over here, so they get on Central Time Zone. These people stay on Eastern. The tip of Texas, okay? I think El Paso, Texas is somewhere in here. They do most of their stuff in New Mexico. They're right there at New Mexico. Most of the bigger cities in Texas are way over here. They're not going to drive over there. They're going to just go up here. So therefore, the very west part of Texas is on Mountain Time Zone. The rest of it is on Central. In Nebraska, these areas here go toward Denver to do their shopping. So they will be on Mountain Time Zone, whereas the rest of Nebraska will be, oh, I'm sorry, there's Nebraska. I'm sorry, this is Kansas. Same thing here. I can't remember the towns. Denver is in here somewhere. So these go to west to do things. Over here you go east. North and South Dakota, same deal. Here in Idaho, this part is more like Washington, so they go with Pacific Time Zone. This part is more like Wyoming and Montana, so they go on Mountain Time Zone. That's a few of them. Okay. I can't even remember how many time zones Alaska is in because the meridians are getting, meridians are getting closer together, so you cross more time zones more quickly there. But it is on, I think, several. They may have put a whole state on one. Hawaii is, I think, on that same one. Let's just make a guess here. There is Pacific Time Zone. And this would be the next one out there. Hawaii would be on probably this one is here. And most of Alaska is probably on that time zone as well. So they probably all stay on the same. Even though the Aleutian Islands, which are still part of Alaska, they go way over here. Okay, and we'll talk about them a little bit later. Okay, so that's what we mean by adjusted for local meridian. They're approximately 15 degrees apart. Not exact, but approximate. Adjusted for local conditions. Okay. Now, it seems like to me, at one time in the past, I don't think they do this anymore, Arizona didn't go on daylight savings time. They would go on mountain time one part of the year, and then when they went on daylight savings time, they went on the other. They went back and forth, so they didn't have to change the clocks. And I think some part of Indiana may have done that too, but I don't know. They may have changed by now. That was a long time in the past. All right, now the second part of this, so every hour you do. So noon here would be 1 o'clock in Atlanta. It would be 10 o'clock in LA. It would probably be 8 o'clock in the morning in Hawaii and Alaska. So things are changing. You're in a different time zone depending on where you are on the planet. But hey, something's got to give. You're later in the day here. You're earlier in the day here. Something has to happen. And that's what we call the international dateline. There it is, 180 degrees. That's out in the middle of the Pacific. No major country is affected by this. Oh, a little bit. The western part of Siberia is affected, and the Aleutian Island chains a little bit is affected. Some of the islands in New Zealand may be affected, and some of these islands, the grouping may be. But generally, it's out in the middle of nowhere. So guess what? On this side, you're on one day. On that side, you're on the other day. That's called the international dateline. Because somewhere it has to meet. When it's noon in Greenwich, England here, it's midnight on one day on this side and the other day on that side. Okay. So, oh, and by the way, I should have mentioned daylight saving time. What they do, they set them ahead in the spring ahead, fall back, 1 extra hour of sunlight during the summer evenings. Frankly, in my mind, that's just so the CEOs can get out there and play golf. Okay? They blame it on everything else. Agriculture and everything else. I think it's all up to the CEOs wanting to play golf. Now, that's my bias. Were you going to say something? I thought your hand went up.
So, like, right now when I call India,
Right.
they're 11 and a half hours ahead.
Yeah. And that's because India has averaged and is not right on a thing. Because they're a pretty good sized country, and they would be part of it in one time zone and part in the other. They average and all get in the middle time zone. So they're a little different. I knew that they were a half hour because they just took an average and went and moved, which you're certainly able to do. So the international dateline is usually right along the 180 meridian. Remember, Greenwich is 0, so half a globe away, international dateline. However, this is also set up so to adjust for local, deal. Like Siberia didn't want one part of Siberia to be one day and the other part the next day. So all of Siberia, they took this, you can see it here, you can see it up there a little bit, but they took this line and zigged it over here to get all Siberia on the same day, but then had to zig back this way to get all the Aleutian Islands, which belong to the U.S. and are part of Africa, of Alaska. They want to get them on the same day. So that's why there's a zigzag up there. This is to include Siberia on its day and include the Aleutian Islands on our day. And then that follows down the international dateline pretty much until you get down here to part of what they call the Samoan Islands. They tried to get most of those on one day, so they jigged over here, but also some of the islands belonging to New Zealand that were on the other side of the international dateline, they wanted those on the same side. So that's why it has those, again, adjusted for local variation. Now, I'll tell you a Navy story. I don't know if this is true, but I've heard it was. Okay? Supposedly there's some island out here in the Pacific, and I'm sure there's several of them, that sit smack dab on the international dateline. And one of these islands, I guess, is one that the naval vessels at least went to occasionally. And because they did, this really clever entrepreneur built him a bar, because of course the sailors go to bars, right on the international dateline. So half of the bar is on one side and half of the bar is on the other side. So therefore on Saturday night, on one side, he had to close when it got Sunday morning. But on the other side, it was already Monday morning. So he could then open up over here. Supposedly that he did that and kept the bar open constantly. I don't know if they really let him get away with it, but that was his plan. So he'd never have to close the entire bar all night long. Whether that actually happened or not, I'm not sure. It makes a good naval story, though. All right, any questions on how we do our time zones? Like you said, India and other countries may, if they stay on one time zone, may split it and go half-hour difference. All right, let's move to yearly time. That was all talking about daily time. Solar day, sidereal day. Now, again, we have two types of years. And guess what? The sidereal year is based on the stars. Sidereal means stars. Interval between two consecutive alignments of the Earth and the Sun relative to the stars. It's about 20 minutes longer than a tropical year. Well, what's 20 minutes out of 365 days? Not much. But what the tropical year is the interval between two consecutive spring equinoxes, when the sun is directly overhead your Tropic of Cancer. When that occurs, one at the same location, 1 year to the next, that's a tropical year. Again, that's based on the sun. Well, wait, why don't they call it a solar year? I don't know, but they call that a tropical year. The sidereal is regarding the stars, it's a little bit longer, whereas a sidereal day was a little bit shorter. A sidereal year is just a little bit longer, 20 minutes longer than a tropical year. Now, there's also other adjustments have to happen. Okay? If you notice here, the tropical year is 365.24220 mean solar days. What? We're almost a quarter of a day longer. So what do we do every 4 years? What do we do every 4 years? To our calendar. Okay, let's start over this way. Leap year! How do we do a leap year? What happens?
Add a day to February.
What's that?
February has an extra day.
Yes, February has an extra day. Normal Februaries this year, 28 days.
Next year, 39.
Okay, next year is 2018?
No, next
Still
2020.
Huh?
2020.
2020. Oh yeah, that is next year now, isn't it? This is 2019, obviously. Okay, in 2020, we will add a day. In February 29th, just like you said. Now, I've known 2 people who were born on February 29th. So they're very young, you know, because they only have a birthday once every 4 years. No, I'm just kidding. They celebrate either on the 28th or March 1st one, okay, the other year. Okay, so this is why. Because there are 365 and almost a quarter, not quite a quarter, mean solar days. Well, how do we do it that's not quite a quarter? Were any of you, okay, so we'll have a leap year next year, 2020. We had one back in 2016. We had one back in 2012. We had one back in 2008. And we had one back in 2004. Did we have one in 2000? Y2K. Were any of you alive then? Yeah, some of you were. Okay. Did we have a leap year that year?
Kids.
Huh?
We were small. We were small. We were kids.
Oh, yeah, you were very small, so you don't remember. Okay. Let me tell you, we didn't. Because every year that's divisible by 4, 04, 08, 12, 16, 20, 24, yeah, all those are leap years. But centuries that are divisible by 4, 2000, 2400, 2800, those years we will not have a leap year because it's not quite a quarter of a day. So once every 400 years, we don't have a leap year that 1 year. Okay, so in year 2K, Y2K, 2000, we did not have a leap year. There was no 29th of February that year. Okay, so that's how we adjust. Now, I don't even know what they're talking about with leap seconds. There's a little blurb in the book. And it still doesn't make a whole lot of sense. So I'll let you read that if you're interested. Okay. Now, we have gone over 3:15. How are we doing? We still haven't gotten to the moon yet. But, so we may not get to do the lab, start the lab today. I don't think we will. So we'll just continue with the chapter now. But at 5:15, we will stop, and that's when you'll take your test. Okay? From chapter 15. Yeah. Okay. Sorry, long day today. Okay. Now, what we might do is when we finish the chapter, we might start talking about the lab so I can get it in your hands earlier, and then next time, next Tuesday, finish the lab, and then move on with the next chapter. We'll see. We'll see where we pan out. We may not finish the chapter in time today, but let's see. All right. But also at 3:45, stop me because I have to call roll again. Technically, that's left. Okay. So there's yearly time. Okay. One thing that we haven't talked about, and I don't know if there's really a real reason to, is the on table 16.1, we were talking about all the other things. We talked about our day is determined by the spin of the earth, our year is determined by the revolution of the earth, our months are determined by the cycle of the moon. We never talked about why we have weeks. Okay? And I don't know if there's a real reason for it, except possibly Christianity had, or not just Christianity, Judaism and many others had the story of 7-day creation type thing. Maybe that's why there's a week. It's as good a reason as any, okay? But the interesting is how they named the days. And I've never seen this anywhere but in this text. You know where they get the name Sunday? It's the sun's day. The biggest, brightest object in the sky is our sun. The next day is Monday, which is moon's day, the second brightest object in the sky. And you'll see many of the other languages, that's lun, meaning lunar, lunar eclipse, okay? Same thing, named after the moon. The next day, and in English it doesn't make any sense, Tuesday is Mars Day. The other countries' languages here, yeah, you can see Mars in it. In French it's Mardi, Mardi Gras. Gras means fat, basically. Fat Tuesday. Okay? Mardi. Mars. Wednesday, Mercury's day. And you see that the many of the languages that looks a lot more like Mercury, how they get Wednesdays out of that for us, I'm not sure. Okay? Thursday is Jupiter's day, and there's only a few of those that look anything close to Jupiter. I don't see how we get Thursday either. Now, what I remember when I was in school, that we also mixed in some of the mythology from the Norsemen, and this was actually Thor's day. Whether that's true or not, I don't know. Friday is Venus's day, and you see that at least 4 of the languages it really looks like Venus. And then Saturday, that sounds like it's Saturn's day. Okay, that's just interesting little note. Nothing really all that important there. Okay. There are examples 16.3 and 16.4. They get really off onto how many sidereal days are in 1 year. How many? Yeah. This is fun math just to play around with, but I don't know if it really makes that big a difference. But they threw in the problem, so if you're interested in doing that, it's fine. On page 418, they didn't show this in our slides, but there is a picture of what I was talking about of the analemma, which is also called the equation of time, also called sundial, and there it is showing how a little hole on local apparent noon, you have to get that local apparent noon right, make a mark on the floor every day, and you get the analemma. Okay? And that's also called the equation of time. Now, page 419, Science and Society. Are you really saving time when you go to daylight savings time? No, it's just making it so that the bankers can play golf in the afternoon. I don't know why it is, but you can read that and find out about it. Then the example 16 talks about how many time zones between Honolulu, Hawaii, and New York City. You basically subtract the number of degrees or minutes, and for every 15 degrees, you add another time zone, just to see. They say about 6 time zones, so it's 2 more time zones out of California. And then you do the same thing with Denver, Colorado, and the Bay of Fundy in Nova Scotia. Okay. So I think that basically gets us through time. Oh, monthly time. We didn't do monthly time. We talked about it, but we didn't do it. Let's do monthly time. Oh boy. Guess what? There's 2 different monthly times. One is relative to stars. That would be sidereal month. We don't use this. Okay? What that would be, if you us here on Earth, you look at a full moon here, relative to the stars, okay, this position and the moon's position, not full moon, but the moon's position to that same star out here would be what they call a sidereal month. But because we do it from full moon to full moon, the moon's going around us just like we're going around the sun, so that moon moves a little bit more way this way before it's full moon again, and that's about 2 1/6 days difference. About 2 days and another sixth of a day. 4 hours. 2 days and 4 hours approximately for it to move to the synodic month. Now, why don't they call it something else? Why don't they call it a solar month? Well, I guess solar wouldn't make any sense, so they call it a synodic month. So it's about 29 and a half days, and that's why we have our months are right around 30 days. Okay? We have one that's really short, February, 28 days, and the others are either 30 or 31. Okay? So seems like they would make them, most of them 30 and only a few of them 29. That would work out a lot better, but they don't do that. Now, does anyone know a simple, easy way to remember how many months have how many days? Okay. I first learned 30 days, that's September, April, June, and November. All the rest have 31, except for February, blah, blah, blah.
It's easy.
Okay. But this is much easier.
Yeah.
Okay? Start with any knuckle, whichever way you want to do it, and use just these 4 knuckles. January, February. The 31 days are on the knuckle. The short months are in between the knuckles. January, February, March, April, May, June, July. Start back over. Yeah, August. So July and August are 2 consecutive 31-month days. Then September, October, November, December. And then January and December are 2 31-day months too. So using your knuckles, that works. However you want to do it. January, February, March, April, May, June, July, August, September, October, November, December. Then go back to January. Okay, so there are a couple ways to do that. Why they split them up that way, I'm not sure. Okay? Has to be. Now, the synodic month includes the amount that the extra days that it takes the moon to move from full moon to full moon. So that's what we base our months on. The sidereal month really has no meaning at all for anything. So that's why months are based on the moon. Okay. Now, since we had months based on the moon, we enter 16.4, which is now talk about the moon. Okay? The moon is our closest celestial body. It's our little satellite. Only it's not that little. About 380,000 kilometers away, which would be about 200 and... Second? Yeah, I was going to say a little bit less than that, 220 or something like that, miles away. 200 and some odd thousand miles away. Compared to the sun, which is 93 million miles away. So it's so much closer than the sun. Compared to Venus, our next closest planetary neighbor, way closer than Venus too, okay? Then Mars, okay, so everything is a lot more distant. It's characterized by craters. Now guess why there probably are craters on the moon? Because the moon has no atmosphere. Remember what are craters caused by? All those meteoroids hitting the surface. Okay? And because there's no atmosphere to burn them up, they all hit the surface that are going to hit it. They're all going to hit it, and they make all those craters. So I would have put no atmosphere first and then characterized by craters. Now, there's also, besides the craters, you have the lunar highlands and the Maria. Now, what the Maria, where it got its name, that almost looks like the word marine. And they actually did think that the moon had water on it. And these Maria were actually ancient lava flows that from the earth looked like they could have been bodies of water because they were darker, looked like they could have been water. They're not. They're ancient lava flows. Which means sometime in the moon's past, long past, it probably had volcanic activity. None measurable anymore. Okay? Now, we, the U.S., have been to the moon on 12 Apollo missions. Now, did we land 12 times? I don't think so. Well, wait. Let me back that up. Did people land on the moon 12 times? I don't think so. We've landed unmanned spacecraft on the moon many times, but I don't think all 12 of those were. The Apollo missions were all manned, but they didn't all land on the moon. They went to the moon or close to the moon or whatever. There was supposed to have been another one, Apollo 13. Now that wasn't from this 12, that was from another. It was his first aborted mission in space. We've had a couple of blow-ups, bad things. Two shuttles blew up, Columbia and Challenger. Columbia on the ground, I think Challenger when it was trying to come back to Earth. But we had one really close disaster of going to the moon, and that was Apollo 13. Now, I think that the movie Apollo 13 with Tom Hanks and I can't think of some of the other guys in it. I know one of them, but I can't think of his name right now. That probably was pretty close to reality. There's a little bit of Hollywood in it for sure, but that probably was a pretty good rendition of what happened. And it was scary. It was really, really scary. Okay. There's a picture of the moon from your book, and now the moon doesn't quite look like this with lines here. These are where they pasted different pictures of the moon together, and that's why the lines are there. But these are the Maria, the darkened area, and then the lunar highlands are the lighter area. And it's sort of hard to see from this one, but you can see craters all over the place there. It's pockmarked by craters because it has no atmosphere to burn up those meteoroids, which become meteors. Well, they don't become meteors because they don't burn. They become meteorites hitting the moon but not hitting the earth. Okay. I thought they were going to show the Apollo missions. They do in the book, but I thought they were going to put it on the slide set. They don't. It's big. Okay. Now, you might ask yourself, what's in between Apollo 1 and 7? Okay. Apollo 1 was the very first initial attempt. They weren't going to go to the moon. This is the first, when NASA developed the Apollo spacecraft to handle 3 people. Before that, 1 at a time. That's all they could handle. Now they got a bigger one to handle 3 people. Okay? And, all the other things with it. The first one, they were testing it out, doing this kind of stuff. They weren't going to go into space. They probably weren't going to go to the moon. But it was the first. Unfortunately, that one blew up on the ground. The crew died in the spacecraft during a test 3 weeks before they would have flown into space. That was NASA's first major disaster ever. Up to then, they had a perfect record of safety. They lost these 3. Their guys were Gus Grissom, Ed White, and Roger Chaffee. Are any of you from Huntsville? Or ever have any dealings with Huntsville? Huntsville is Space Center, right? Big Space Center. After this happened in 67, the next high school that was built there was, guess what? Grissom High School, named after Gus Grissom. The next, I think it was junior high or middle school that was built, was named Ed White Middle School or junior high. And the next grammar school that was built, I believe, was named Roger Chaffee. So it's Chaffee. So if you go to Huntsville and you see, my wife graduated from Grissom High School. So her brother and her sister, they're from Huntsville. They went to Grissom High School. They remember, and I think one of them or more went to one of the other, Ed White or Roger Chaffee, one of the lower grade. They took that seriously. I mean, NASA was flabbergasted by that. Okay. But the ones that in between Apollo 1 and 7, they had other, may not have been manned, but they were testing the equipment and the things like this. But Apollo 7 was the first Apollo mission in space following the Apollo 1 launch pad fire. So the others were either scrapped or they were unmanned or whatever. Okay? Then there was Apollo 7, 8, 9, 10, 11, 12. 13 was the one that was the first deep space, first abort in deep space. They were way, way away from the Earth. And that lunar module was used as a lifeboat to return. They couldn't take the whole thing back. What was going to land on the moon, they had to drive that back. That was scary. Okay? We skipped to 11. 11 was the actual first landing. The lunar module actually landed on the moon. Neil Armstrong made his famous statement. It was the first manned landing. And then several of the others did land. I'll let you read all those. There was an Apollo Soyuz mission that we partnered with the Russian Space Agency, and their space station was Soyuz, so that's why that's mentioned. That was the first international space rendezvous. Okay. Pretty impressive. Okay. See, I think that's, well, no. Okay. So, what's the composition and features? This is also on page 424 of the moon. Now, let's back up a little bit and remember, the moon has no atmosphere. So, it has been pummeled its entire life by space junk, meteors and other things like this, just hitting it all the time. So, therefore, the surface, which you would think would be rock, really isn't rock. It's dust, fine gray dust on the surface, accumulated from micrometeor impacts to macrometeor impacts. But the glass beads are formed from the melted material because these impacts are hard, they're fast, they produce a lot of heat, and the materials melt and then reform these glass beads. So that's that fine gray dust. 3 meters thick. I'm about 2 meters tall, so the ceiling is close to 3 meters. If you were on the moon and you weren't wearing something like snowshoes, which is what the astronauts use, you would probably sink into that fine, fine dust. But they use big rock shoes to keep you from sinking. Okay? The rocks, the Maria, the basalt, the volcanic rock, they're mostly basalts. I think this is the second time we've run into basalts. Don't sweat it. We'll find out what a basalt is next chapter. That's coming up soon from books near you. Okay. Formed from the molten lava. That's exactly what basalts are, formed from molten lava. Now, you have light-colored highland rock. Remember the highland rock? Those are lighter colored. Those were formed about 4 billion years ago. Okay? Now, how long do they think the sun has been around? No, it will be. It's been 5, and they think it has 5 more years. So the moon didn't seem to have been formed until about 1 billion years after the sun was. Now, we don't know exactly when the Earth was formed, but it probably was in between that 0 and 1 billion years, okay? The 5 billion and the 4 billion, okay? Now, that light-colored highland rock is a lot like our light-colored rock, which we'll do in the next chapter, our granites and things like this, which are mostly siliceous, silica, not iron-based. The salts are iron-based, the silica are the lighter rock, okay? The darker colored Maria, those rocks range from 3.1 to 3.8 billion years. Now, hang on to those years. We're going to find those are important later. What this means, these are the volcanic rock. So about 200 million years after it was formed, it started having volcanic activity that lasted about 700 million years. And since then, we haven't had very much volcanic activity at all. So this is where the basalts, the molten lava, the dark-colored Maria rocks came into being when you had volcanic activity. Now, what's the internal structure of the moon? Now, this is interesting. For about, 3 meters are gray dust. For about 65 meters down to twice that, about 130, not meters, kilometers down, to 130 kilometers down, this is your outer rock. Now here is another weird thing. This outer rock is thicker on the back side of the moon, far side of the moon, thinner on the side that we see. Okay, now wait a minute. We only see one face of the moon ever. We, Earthlings, have never been on the other side of the moon. The astronauts have. They've seen that side of the moon. We haven't. Every time you see the moon, you're looking at the same side. And the outer rock is thicker on the back side, the far side. Okay? Then somewhere about 900 kilometers down, you have partly molten iron core. And that iron is where the lava came from back 3.1 to 3.8 billion years ago when they had volcanic activity. So that's where the dark Maria rock, the basalts came from, molten iron. Okay. So it still has a molten core, but it's not very active. No volcanoes. All right. So with these in mind, we're going to go to the next, and we're going to look at the history of the moon. Now, there's an error on this slide, a couple of them, okay? I'll make those corrections as we go, okay? Stage 1 was the origin stage. Now, here's what the current thought is, and lots of evidence seems to support this. It was formed from material ejected from a collision of some enormously large object with the Earth. Yes?
354.
What's this?
354.
354. Huh? Oh, okay, got it, okay. I thought you were telling me when this was, and I thought, how did you know that? No, okay. All right. Yeah, I'm sorry, this time slipped up on me. Let's get it. Zaria is still here, I can't talk. Marcus never made it in today, right? Marcus hasn't made it for several days now. Rod is still here. Gavin hasn't made it in yet today. Bertram still hasn't made it in. Bertram is on shift work. He'll be here, I think, next week. Okay? Melanie didn't make it in today. Sonia is still here. I'm sorry, I mispronounced it. Samaya. Goodness gracious. Corey is no. Is that Corey's stuff? Okay, so maybe he is still here, but I don't see him. Thomas Earl is mostly here. Okay. Derek didn't make it in today, did he? We haven't seen Derek since the very first day. I've never seen Derek because I wasn't here the first day, but he was. Okay, Seth is, yeah, over there. I saw you. Rashad is here. Kayla's still here. Cole still here. Yep. Patel's still here. Reggie, have we lost him? He was here. Is that his stuff right behind you? Or is that your stuff? That's Reggie's. Oh, that's his. Okay. So we may have lost Reggie. Diego's still here. Thank you very much. Michael Thomas. I saw his name on the monitor down there, but he hasn't made it back. And Radeja is still here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 2, 4, 6, 8, 10, 11. Okay, got it. Okay, y'all need to take a little break. Would you like one? Yay or nay? Would like a break. Let's try to keep it less than 5 minutes. I probably just need to rest my voice for a little bit. Thinking I'll fool my stomach into thinking something's in it. So I have enough to go on, by the way. So it's fine. All right, now let's look at the history of the moon. Okay? Stage 1. Now this is the theory. This is what the current faults are. And much of what we've already talked about supports this big time. They think that the moon was formed by some major collision with a large object and the Earth. Now, if you were to go back and look at sort of the timeline of the planet's formations, you probably, I don't think they ever told us exactly, but for a long time the planets were, material that didn't quite make it into the sun, but it was still hot, molten material. If this collision occurred when we were still sort of a semi-liquid state, molten material, and stuff like this, then it would have been easy to break off part. If a big collision, then a part broke off and started orbiting around. Now, remember, the same side of the moon is always facing the Earth, meaning that was once a part of the Earth. There was no reason for it to have any spin, so it just is circling like that. Now think back, the other thing we've heard. The back side of the moon is thicker than the front side, the surface rock. That kind of makes sense. If it had been thrown it out there, the heavier, I guess it's the lighter stuff would have been thrown further and the heavier stuff stayed close. So that sort of makes sense, that the thicker part is further away. So that's where we think it happened. And if you go back and check, we were probably formed, in that first billion years of the sun too, and that was shortly after that is when the moon was formed, from what we saw in the last slide. Okay, stage 2. Shortly after we were formed, that major collision caused a lot of heat, and if we weren't already liquid, the stuff became liquid. That's when the surface was still molten. That's when it was still forming, and the molten surface was about 100 kilometers deep. Right, let's go back here. The outer layer is between 65 and 130 kilometers of outer rock. That's probably about what we're talking about here, 100 kilometers deep. That was molten. 200 million years after formation, okay, that makes sense. 3.8 from 4, that's 200 million. That is the molten stage, about 200 million years after the formation. The heating was from the solar system debris impact. Remember, the solar system is still, when it was forming, the sun was forming, there were explosions and things, before it ever, settled down. And things were getting thrown around. There was a lot of radioactivity. There was all sorts of mess going on. And that's where the heat came from, the solar system debris impact. It was finally settling down after about 200 million years or so. Stage 3, the molten interior stage. Molten interior. The outside began to solidify, but the inside was still molten. Accumulated heat from radioactive decay, remember that was still going on, friction, that kind of stuff. Now here's where the errors are. This has to be, began 3.8 billion years ago, ended about 3.1 billion years ago. Why? Because that makes sense here, 3.1 to 3.8 billion years old, okay? Now that's one piece, but if you look in your book, you'll see that stage 3, you'll see it is 3.8 and 3.1 billion. So whoever the typesetter was here messed up. He put million, that should be billion. And that would be billion down here as well. Okay? So here, after the surface began to solidify, you still had molten interior, and during that, when the interior was molten, that's when you had the volcanic eruptions. 3.1 to 3.8 billion years. That's when the lava flows. That's when the Maria were formed. Okay? Now, it's 4 billion years old, 3.1 billion till now, been very quiet. Got over its initial activity, its volcanic activity, everything else. For the last 3.1 billion years to present, it's been pretty much cold and quiet. Not much going on. Still gets hit by meteors, micrometeorites, meteorites. It gets bombarded with that. Of course it does. That's why the first 3 meters are dust, because it's just been pummeled by that stuff, okay? But no major activity since then. So it only had a lot of activity for the first 200 million years, then volcanic activity for about 700 million more years, and then for the last 3.1 billion years, basically almost nothing going on. So it's been pretty quiet most of its life. Now, I have heard that there are things like moonquakes. It still has tectonic shifting going on, but they're not resulting in volcanic activity like that does on Earth. We'll get to that in a later chapter. Okay, make sense? Any questions? Okay. Now that's the moon itself. Now let's talk about the Earth-Moon system. This is 16.5, which I think is that is our last section. Okay. Now, the moon to Earth mass ratio, I've said this I don't know how many times already. Mass ratio is the highest in the solar system. I mean, no matter how big Callisto and Ganymede and those others are in Jupiter, their moon to mass ratio, Jupiter's mass is so big, that moon to mass ratio is tiny. Okay? Saturn, even though Saturn is not a very dense planet, Titan and those other big moons, moon to mass ratio, tiny. Okay? Even small little Mercury that has 2 moons, its moons are so small, nowhere close to what Earth is. There's no other planet in our solar system that has a moon nearly as big relative to our size as our moon. We're really unusual that way. Now, here's how big it is, okay? You are supposed to say, how big is it? Well, here's how big. The diameter is about 1/4 of that of the Earth. So if this is the Earth, this diameter is from here to here, let's say that far, it would be about this. That would be the diameter of the moon. It's quite a bit smaller than Earth, but way bigger than any other moon of any other planet. Now the mass is only 181st that of the Earth. Well, because the mass depends on the density of the Earth is greater, and that also depends on volume, and for a quarter of the diameter, that would be 1/4 times 1/4 times 1/4, because it depends on the radius cubed. So that would be 1/64. So if it's taking just by size, it would be 1/64, but by the fact it's less dense, it's only 1/81st. So it sounds a lot less, but still way bigger, bigger mass ratio than any other moon for any other planet. Okay? Now, how large is it? It's large enough to affect the Earth's orbit. Okay, on this next slide will show this. I mentioned it before when we talked about relative motions. If the moon were just a negligible mass, like most of the other moons are for most of the other planets, they could go around the Earth and the Earth wouldn't even notice, hardly. Okay, they just go around. But because our moon is so big, and that seems small, but it's a significant mass, that means that the Earth-Moon center of mass is somewhere here. It's certainly closer to Earth than it is the moon, and we revolve around that. So every time the moon goes around us, then part of the Earth goes around the center of mass too. So the moon is going out here, and the Earth is doing like this. It's not moving much. The moon's moving much more, but the Earth is moving. So therefore, our orbit around the sun is sort of wobbly, because wherever the moon is, that's making us shift a little bit. Okay? So that's the effects of having such a large moon. It makes our travel around the sun a little drunkardly. Okay? Not really, but something like that. All right. Now, the moon also has phases. Now, this is what a whole lot of today's lab, not today's lab, whatever, the lab for this chapter will be talking about the phases of the moon. Okay? Not all, but a lot of it will be. A whole lot. Okay? And what you'll be doing at home, part of that will be looking at the phases of the moon. So this is an important part of this. Now, this is a result of changing relative positions of the Earth, Sun, and Moon. Okay? Well, this next part of the slide is going to be really important for what we're going to do in the lab. So I may bring it back when we do the lab, but this is important. So let's talk about some of these phases of the moon. Okay, here's the Earth, right? Tail's going to be Sun again, right? Okay. Now, where do you want the moon to be? Pick a place. Over here. Okay, so we'll have the moon right here. Okay. This half of the Earth is being lit by the sun. This half is nighttime. No light from the sun. We can see stars back here. Again, over there. Moon's over here. Is that where you wanted it? Moon's over here. That half of the moon is being lit by the sun. This half is not. So when we're here on Earth, on the backside, looking out and seeing the moon, we see about a half moon. The side toward the sun is lit. The side that's back here with us is not lit. So let's start somewhere else. The new moon. On the new moon, the moon is here, in between us and the sun. Now, most of the time, it's not in between us. It's up here or down here or somewhere like that. But all we see is the dark side of the moon, meaning we don't really see it. And when do we see that? It's mostly in the daytime, because that's when the sun is over there. That's when the new moon, we don't even notice it or don't even see it, because the new moon is so dark, because half of the moon being lit is toward the sun. The first quarter is when it gets over here, and we see half of the moon lit and half of it not lit. Okay? That's called the first quarter moon. Okay? The full moon is when the moon's back here. Now, we're being hit by the sun, but back here, on this side of the nighttime, we see all that side of the moon lit by the sun. So that's a full moon. So the phases of the moon nothing to do with curvature of Earth, nothing to do with not much to do with curvature of the moon. It's the fact what part of the moon is being lit by the sun. And when the moon's back here, all of it's being lit. Okay? The third quarter moon, or last quarter moon, which would be the third quarter, that doesn't make sense in football, is here. Again, this back side is dark, the front side is lit. So it's another half moon. Okay? And so new moon, first quarter, full moon, last quarter. We also call those half moons as well. Now, the strange thing is, no matter what you got here, the half of the moon that's facing the Earth, half that's lit, half that's not, that's the same side. It always is the same side of the moon facing the Earth, no matter where it is around us. That indicates that it probably was separated from the Earth. It was part of the Earth. Okay? Now here's the illustration, and we will see this one in our lab. I don't know if we'll get to it today. What is it now? 4:20 approximately. Okay, so we just got an hour more, less than an hour more before the test time. Okay. The one thing different, in our lab, the sun is over here and the system is over here. Earth in the middle. Now this shows the moon way too big, but it just shows it for illustrative purposes. The side of the moon, or the Earth, everything that's toward the sun is lighted, everything on the back side is dark. Night. Okay? Now, the lab we'll have moons in here, and here, and here, and here too. It'll show 8 portions of the moon. This is just showing these quarters. The new moon, that all you see from the Earth is, and you only see it in the daytime, is the dark side, so you hardly see it at all. First quarter, you'll see it from nighttime here, but you only see half the moon lit. Okay? Here will be a full moon because everything facing the Earth will be lit. Over here will be the last quarter. Okay. All right. This is what we'll base most of the lab on this week. This very type thing here. All right. Now, whenever you see, this is called a crescent moon, and we'll talk about that in the lab too, because it forms a very small crescent. You know where the sun is. Take these 2 points perpendicular to that. The lighted side of that's toward the sun. The sun's down here, somewhere, way, way down there. This is just past the new moon, or just before new moon, or just past the new moon, where you just see that fine, thin little crescent. This will be either just before that sunset, after sunset, or just before sunrise. You'll see that. You won't see it much later in the night. Okay. Make sense? Okay. Ooh, we just had one last Sunday, right? The eclipse of the sun and the moon. Now, what that means, something gets in somebody else's way. In other words, in the shadow. Now, the moon's orbit is inclined about 5 degrees from that of the Earth. Now, that doesn't sound like much, does it? But remember, we're 300 some odd thousand kilometers away, so 5 degrees, you can be pretty far out there, right? Okay. Now, to get an eclipse, you need the proper alignment of the Earth, Moon, and Sun. So let's go back to our situation here. Sun, Earth, Moon's out here somewhere. Inclined at 5 degrees, so it's not here, it's either down here or up here. Most of the time, it's not right in line. So most of the time on new moons, it's up here or it's down here, but it's not in line with directly in line with the sun. Even full moons are either up here or down here, but they're not directly in line with the sun. Okay? Because of that 5 degree tilt. Okay? But every now and then, let me do the slide. Okay. How I wish they had improved on this slide. 2 ways, really. it seems like to me, if the sun's over here, okay, and the moon's there, and the shadow is back where it shows there, they should have made this light colored, not dark colored, because this is the bright side. This is the lighted sun of the side of the moon. But if the moon makes a shadow like this, the earth makes a shadow like this, because the earth is much bigger than the moon. Okay? Does that make sense? And this is the sun out here, so the shadow is back there. But the shadow is getting narrower, because the sun is so big that parts of its rays are coming in either side, so the dark part of the shadow is very narrow. And it gets narrow as it goes. It's supposed to be shaped like that, like a cone, very long cone. Okay. Now, here's the deal. The conical shadows, that's what I said, shaped like a cone, have two parts. There's the umbra and the penumbra. The umbra is this dark part that I've drawn in here and that shows here. The penumbra goes like this. It's wider, but it's only a partial shadow. Same thing with Earth. It has a wider penumbra. Narrow umbra that gets smaller as it goes, but wider penumbra that gets a little wider as it goes. Okay. So the umbra is the inner cone, complete shadow. The penumbra is the outer cone, which is only a partial shadow. Now, most of the time, this is the plane of the Earth's orbit, which is basically the ecliptic of the sun. This is the plane of the moon, which is tilted. Okay? Now, those two planes only intersect twice a cycle, twice a month. Now, if they intersect here and the shadow of the moon goes back here, you don't get an eclipse, because the Earth is never in the shadow of the moon. Okay? And like right here, this would be a solar eclipse. Right here, if the moon's back here, that's the only time you'll see a lunar eclipse, was when the Earth's shadow is where they intersect. Out here, it's not in the Earth shadow at all. Okay? Even though it's behind the Earth. So you won't see a lunar eclipse either. That's why it's really rare to see a lunar eclipse and extraordinarily rare to see a solar eclipse. Now, I haven't gotten to those yet, but I'm just giving you the ideas. Okay? The solar eclipse is when this point right here is over here. Twist this around so that the shadow of the moon does touch the Earth. Now, last fall, wasn't it? October of last year? May have been? No, earlier than that. August of last year, I believe it was. 18. No, not 18. 17. Sometime fairly recently, we actually had a solar eclipse. We only got part of it because we were in the penumbra and a little bit in the umbra, but not much. But Nashville got the whole thing. In fact, from somewhere in Georgia up through Nashville, and I think going as far as Oregon, I think Jackson Hole was in it. You know, there were a lot of places that was in it. They got a full solar eclipse. That's when this position here was twisted around so the moon's shadow just barely hit the Earth's surface. Okay, when the umbra actually made it to the Earth's surface. That's what a solar eclipse is, where the tip of the umbra touches the Earth. Now, remember none of the planets have perfectly circular orbits. They're all elliptical. Same thing with the moon. There are times when the moon is close to the Earth and the time when it's further away. That's what makes an ellipse. This last lunar eclipse we had last Sunday, that was also one of the biggest moons. That's when the moon was closest to the Earth. But then the moon was back here in the shadow of the Earth, And that was when we had the total lunar eclipse. And that's why it went on for, what, an hour or longer, because we were in the shadow of the Earth that long. But it was a big, beautiful moon at the same time. So the solar eclipses are only going to happen when it's a new moon, and the lunar eclipses are only going to happen when it's a full moon. And it was Sunday night. Okay. Now, when the moon is further away, not close to the Earth, but further away, the tip doesn't quite touch the Earth. The tip of the umbra doesn't quite touch the Earth. And when that happens, we see an eclipse in the center of the moon eclipses the sun in the center, but there's an outer ring of brightness. That's called an annular eclipse, when the umbra doesn't quite reach the Earth, but you see a ring around the shadow of the moon. That's part of the sun that is because it's not all in the umbra. Okay, so the lunar eclipse, or when the moon is back here in the Earth's shadows, but it has to be twisted around so it's on that crossing of the two ecliptics, the sun's ecliptic and the moon's ecliptic. They have to be in line. So they don't happen often. Okay? They do not happen often. Here is, I think, a little bit better illustration. Let me erase these other lines. This shows the umbra and the penumbra better. Now, the distances are not right, and the relative sizes are not right, but not too bad. They just do it for illustrative purposes. The sun, huge out there, the umbra is where both all the rays coming in here are blocked and all the rays coming in here are blocked. This is complete shadow here. Up here, this is the penumbra. Some of the rays from here come through, and some of the rays from here come through. But the umbra, everything's blocked. Now, lunar eclipse, total lunar eclipse, will happen when the tip of the umbra actually touches the Earth's surface. This is a solar eclipse. The annular eclipse is when the moon's a little further away, the tip is somewhere right here, doesn't quite reach, then so nothing is in, so the outer part of the sun is visible. And that's what they mean, the annular eclipse. You have a little ring around the moon, basically. Bright, bright ring around the moon. That's when the moon is too far away for its shadow to completely hit the Earth. Now, take this on the back side, continue drawing the Earth here, and you see it has a huge shadow, and it's quite often, not often, but it's quite possible for the moon to pass through the umbra of the Earth, because the umbra of the Earth goes far longer than the umbra of the moon does. And that's what we had Sunday night. The moon passed through, it took an hour to go through the umbra of the Earth. Because the Earth's shadow is big, goes a lot further, and the moon just hasn't passed through that. That's what we saw then. Does that make sense? Everybody? Anyone need this any longer? All right. Other ways that the moon and Earth interact, and the sun's involved with this. Before we go any further. And by the way, that one graph that we saw on the slide a few minutes ago, it's in your book too on page 426. And we'll be referring to that when we do the lab next time. Or whenever we do the lab. Yeah, it will be next time, I think. There are mistakes and misunderstandings. This book really loves these. Here are some moon mistakes. Is a common misunderstanding that the Earth's shadow creates the moon's phases. No. That's the part of the moon being lit by the sun. Okay, I already mentioned that. The phrase, a blue moon, has nothing to do with the color of the moon. Okay? Remember this. I'm going to flash back, literally, on my slides. Okay? There it is. One synodic month happens every 29 and a half days. But guess what? One, two, three, four, five, six. 7 of our months have 31 days. Okay? So that means that the moon will have 2 phases, one very early in the month and one very late in the month, the same phase. Every now and then, that will be a full moon. That early in a month, a long month, it'll have a full moon. And then later in that month, right before it changes to another month, it will have another full moon. Because it's 29 and a half days in between the full moons, right? And that can happen, not often, but occasionally in a 31-day month. Barely happen in a 30-day month, but it can happen in a 31-day month. When that occurs, there's 2 full moons in 1 month, one very early and one very late. We call that a blue moon. So that's what the phrase is, once in a blue moon. Doesn't happen very often, okay? In fact, it usually takes years for that to happen, okay? So that's what it is. It has nothing to do with the color. And then it says here, and I'm not sure about this one. It says a popular myth has more accidents happening during the full moon phase. However, studies have found no statistically significant relationships between the accident rate and the moon phase. This myth is probably a result of people remembering the full moon if there was a full moon that night and they never noticed what the moon was if it's not a full moon. Okay. Now, that said, have any of you ever worked in an emergency room or known someone who worked in an emergency room? Maybe not. I've had several people in my classes before when this has come up. They say, hey, we're always busier in a full moon. I don't know why, okay? It may not be accidents. I don't know why. But we had a wacko neighbor one time. This guy had some screws loose. Or as my younger brother used to say, he was a few bricks shy of a load. Okay, there was something wrong. He just would go off every now and then. He would put acid on another neighbor's car. He threw rocks through 2 picture windows of ours, huge. He just would do weird things. He one time claimed that a neighbor's dog had bitten him, but the neighbor had not been there all day, and their dogs were out on the patio where everybody could see it. But the patio was up on the 2nd floor. So there's no way those dogs could have bitten this guy that day because everybody saw them up on the patio all day long. The neighbor wasn't even home. So we started calling them the pole climbing dogs. They climbed down the pole, bit them, and climbed back up. Of course, that didn't happen, okay? But it did happen that Corey showed back up, so that's good, okay? We haven't seen Reggie yet again, so I guess he's not there. All right. But we started noticing, now maybe this is like here, it seemed like that guy went nuts about every full moon. I swear. I mean, my wife started noticing. And they say, well, maybe it's just because on full moons you notice the moon. Well, no, it was about, not every month, but it always seemed like it was near a full moon. So I don't know. I do not know. He says it doesn't, but we'll see. All right. Now, the next thing we've got here is a table about the eclipses. The total solar eclipse, we had one back in August 21st of 2017. That's the one I was talking about. It was not this past August, but the year before. We had just started. We had only had like 1 or 2 classes, maybe not even that, of this Physical Science 111. I said, we got to go out there and see the thing. So we did take some class time to go see the eclipse. Okay, it happened during class time too. Total lunar eclipse, starting back in 2014. There were 2 in 2014, 2 in 2015, none in 2016, none in 2017, one in 2018, and then we just had one January 21st, 2019. All visible. Everywhere in the U.S. you can see that total lunar eclipse. Notice the solar eclipse? Small paths. Small paths. Because the umbra of the moon is very tiny. The umbra of the earth is very big. Okay? The next one we'll have will be 2 years from now. I'll probably be retired by then. Okay? I'll be 70 years old by then. Then one a year after that, and 3 years before we have the next one. Okay? So they don't come very often. Even the lunar eclipse. The solar eclipses, these two here, 7 years apart. And they're not always visible everywhere. But this is only in the U.S. There will be more eclipses, but they'll be somewhere else on the earth. Okay. The next one in 2024, which is quite a long time from now, that will be from Texas to Maine. So we might be able to see more of that. All right. Now, right at the bottom of page 427, we get to... Ooh, I went way back. I'm sorry, I forgot to advance back up. Tides. What do the tides have to do with the moon? Moon, our closest neighbor, remember? It has a strong enough gravitational field. It pulls the water, because the water is liquid. It doesn't take a fixed shape. It pulls the water toward it on the earth. That's what gives us a high tide. A low tide is when the moon is 90 degrees from there, and it pulls the water over there, making us have a low tide. Okay? This is a result from the different gravitational pulls on the front and back side of the earth. Now, the moon's not the only culprit. The sun, because it's so massive, it has a little bit of a pull too. The moon has the great pull. And that's why, have you ever looked at your calendars that had the tides on them? The fishermen do this all the time. Any of you fishermen? Okay. Not as many as there used to be. Okay. Supposedly the fishing's better at certain tides. Okay. Now, there's 3 factors that make up how strong these tides are. One is the earth, moon, sun positions. The spring tides are when the strongest tides. That's when the globe here. I'll face a certain direction here. Okay? So let's say Gulf of Mexico. Okay? Sun's there. If the moon's there, in line, it's going to pull. That's going to be a high tide. We're going to call that the spring tide, when the sun and moon and earth are all in one line. Or when the sun, moon, and earth are like this. Okay? Because here, the moon is pulling the water this way, sun is pulling it that way. That would be a spring tide. Okay. The neap tides are when the sun's here, the moon's here. So that's going to be, might be a high tide, but it won't be as strong a high tide as it was when they were aligned. So the spring tides are the strongest, the highest of the tides, and the lowest, by the way, when they're on the opposite way, when they are aligned, and the neap tides are when the sun and the moon are 90 degrees from each other. Now, everything in between is some variation of that. So that's one factor. The second factor is the elliptical orbit of the moon. The greatest pull, of course, is when the moon is closest. That's called the perigee, and that's what it was. Sunday night, the moon was very close to the perigee. It was both a full moon and closest to the earth. The less effect at the apogee. So when the moon's farther from the earth, the tides won't be as strong as they were at the perigee. Now, there's a 48,000 kilometer difference, which would be about 25,000 miles, or maybe a little bit more than that, difference in those things. So that is going to make a big difference, okay, or some difference. Now, the other thing that factors into how great the tides are has nothing to do with the moon, except where it's located. It's the size, shape, and the depth of the water basin. Now, our closest big body of water is the Gulf of Mexico. That happens to have the least tidal effect of anything, of any great body of water. The Gulf of Mexico is one big, fairly shallow bathtub, okay, down there. It doesn't have any shape to it that would create a large tide. So it's only about 1/3 of a meter. That's a little over a foot. So between high tide and low tide, you don't have a lot of difference. Look at this. The Bay of Fundy, which is in Nova Scotia. Here's Nova Scotia right here. If I can find it. Yeah, Nova Scotia is right here. I think this is the Bay of Fundy here. It's that bay that cuts up into the Nova Scotia like that. The shape of that, the depth of that, everything about that makes it so that 15 meters difference in low tide and high tide. What's 15 meters? What did I just say? This room's about 3 meters tall. So 15 meters would be a 5-story building. That would be the part of the building down there that has 3 stories, and then this one on top of it that has 2 stories. That would be the range of tides, the range of high and low tides. I don't know how you even live with that. Where do you dock your boats? If you must have a long ramp that goes there, and the boats must go up and down a pole. Otherwise, they would be grounded half the time, and I don't know how you live with that. That is an enormous tidal difference. Okay? Now, here's what it's talking about, the Earth, Moon, Sun positions. Okay? Let's say the moon is over here. We're going to leave the sun out of it for now. When the moon is over here, the gravitational attraction pulls the water more. That gives you a high tide here. That means on these parts of the Earth, the other sector of the Earth, the tides are the least. There's low tides there. But when it pulls the water here, it also pulls the Earth a little bit, leaving you a tidal bulge on the left behind portion. So you have high tides here and here, low tides there and there. Okay? Now, when the sun lines up with the moon, the moon's here and the sun's here, that gives you your spring tide. When the moon's here but the sun's up here, then that pulls a little bit of the water this way, giving you a neap tide. It is a high tide, but it's less, much less than the spring tide. And if the sun were back here and the moon over there, that would be another spring tide, because the sun's pulling this way and the moon's that way. So you have higher high tides here and greater neap tides there. Okay. All right. Make any sense? Now. Whoa! That's our last slide. Before we get to the last slide, though, there is a couple of examples here. And again, it's just sort of making up some problems so you can do some math. But these are based on formulas that we would have done in the first half of the book, which we haven't done. So we're not going to mess with that. It is pretty interesting to read and see their answers. How far away is the moon if a reflected light beam takes 2.65 seconds to travel from the Earth to the moon and back again? That would be 397.5 kilometers. No, 397,500 kilometers. Now, the guy they have people behind the science here, it's sort of interesting they have him. He's one of my older brother's favorite people of all time. His name was Carl Sagan. Do any of you remember him? He had a show on public television called Nova. But he died back in, I can't remember when, probably before y'all were old enough to watch it. He died in 96. So y'all probably wouldn't remember anyway. My older brother was fascinated with Carl Sagan. He was a good physicist, a good scientist, a good astronomer. Not exceptional, but what he was a fantastic science communicator. He knew science. He knew it so well, but he also knew how to communicate. Sometimes those don't go hand in glove. Like Isaac Newton was a great physicist. I have a feeling he wasn't a particularly great communicator. He may have been. I never knew him. But Carl Sagan was fantastic at communicating scientific ideas in really good ways. Now, he did a lot of good things, and you can study this. You can write on him. Guess what? This can't be your source. You're going to have to get outside the book to get your source. But I did want to mention him and what some of the things he's done. Okay? And as I say in every chapter, nothing takes the place of reading the chapter. So please read the chapter. When you've gotten that read, maybe a time or two, try to read the summary. The summary condenses. It's like the Reader's Digest condensed version. And this is a pretty long summary here. So there's a lot of different materials going on here. A lot of the italicized words or definitions or phrases are the ones to focus on. Then you'll see your key terms, and this is more than most on this too. A lot of these are the italicized words from the summary, but it gives not just, it gives them in alphabetical order, but also gives the page number where they're first defined or described. But then the best thing to study for your test, now this test will be coming up Tuesday, the last 30 minutes on Tuesday, we'll have the Chapter 16 test. Okay? And there are 47 multiple choice questions there. Great things to study. You won't see these exact questions on the test, but there'll be questions covering the same type material. So if you got these down, you're well on your way to mastering the material. Now, questions for thought, I don't think I've seen another chapter that had 30 questions for thought. So these are good to think about. For further analysis, that's about normal, around 6. Invitation to inquiry, you might want to look into that in case you want to do something. I think probably that's going to be pretty close to what we're doing. Yeah, you can do it if you want to. The parallel exercises are more like the examples we've had. We haven't been doing many of those, so if you want to do some of those for your own cultural enlightenment, that's up to you. Okay, how are we doing on time? Okay, we've got about 20 minutes left. Little 25 minutes left before we'll do the test. So let me just briefly go over how we're going to go from here. 25 minutes. I could give out the lab to those who are here, start explaining what you're going to be doing in the lab, and this lab will take you, since we just had the full moon back on Sunday, we have just a little over a week of the moon being visible at that time of night when it was full moon before. So what you need to do is observe the moon for about a 2-week period. And you don't have 2 weeks to observe it now. So what you can either do is start observing it now and then have a 2-week period where you can't see it, and then start observing it again later until you fill up the time. Till you make enough observations. Or you can just wait until the moon first is visible at the time of night you're planning to do it, and then watch it for the next 2 weeks. So either way you want to do that. I can start explaining that to you with the lab now, or we can wait and do this Tuesday. If we do that, then we should start on Chapter 17 now. So you want to start on the lab now and then just start 17 on Tuesday, or do you want to start 17 now and just do all of the lab on Tuesday? I don't care. Which would you like to do? Lab now or Chapter 17 now?
Chapter 17 now.
You want to start 17 now? Is that what you said? Okay. And that way we'll just hang on. I've got the lab ready, but we'll do that. And so here's how it'll play out then, now that we've made that decision. We'll start with 17 now. We're not going to get very far. We only got about 20 minutes or so. But we'll start 17. 17 starts sort of a new deal. It's the geology part. Up to now, we've been the astronomy part. So this is a new section, geology. Okay? We'll have about 4 chapters on it. Okay? At least, maybe a few more, but that's basically it. 17, 18, 19, and 20. Okay? Then we'll have weather, weather and climatology, that's 1 chapter, and oceanography, that's 1 chapter. So that's how the whole term's going to go. Now, what we'll do is get started on 17 now. It won't be very long, just get you introduced to it. Then Tuesday, we'll do 2 hours of 17. We probably still won't finish 17, but we'll get 2 hours of 17. Then we'll stop and have 2 hours of the lab. It's not going to take us 2 hours, but I'll give you 2 hours of the lab. And then we'll do 30 minutes for the Chapter 16 test. Okay? Sound reasonable? Okay. So you'll probably get out a little early on Tuesday. No promise there, but possibly. So since we're at the end here, let's go on and get out of this and get out of that and go to chapter 17. It'll open one of these days. Okay. It's 4:53. Okay, so we got just under 20 minutes. Okay. No, a little over 20 minutes. Sorry about that. All right. Chapter 17, beginning the geology part of it. We're going to start, as you might think of geology, with rocks and minerals. That's the name of the chapter. The strange thing, though, is the book presents it minerals and rocks, okay? But it sounds better, rocks and minerals. But we are going to do minerals first and then do rocks, okay? Now, here is the core concept of this chapter. Earth is a dynamic body. What do we mean by that? Dynamic. It's always changing. Now, the changes aren't rapid most of the time. They're usually fairly slow, okay? But it is always changing. A dynamic body that cycles the rocks and minerals through ongoing changes. Now, we're just going to hit on the tip of this for now because the next few chapters explain better how these changes happen, okay? But we will talk about the changes now. We'll talk about this particular rock later in the chapter 12, but this is the prettiest picture of it. This is one of the oldest rocks ever discovered on the planet, okay? It is a type of what we call a metamorphic rock, which we'll get in the last part of the chapter. How you know that? It was one time a sedimentary rock, and all these layers that you see here were at one time horizontal layers. That's how things settle out, horizontal. But over time, temperatures, pressures, stresses, strains, and things have made this weird looking. And it's a beautiful example of an ancient metamorphic rock. Okay? This happened over a long time. So this rock went from being igneous rock to sedimentary rock to metamorphic rock over long periods of time. The Earth is a dynamic body. Okay? Now, the first section here deals with the Earth, the solid Earth materials. What is Earth? Earth is a non-uniform distribution of matter. Okay? What do we mean by that? Most of the surface rocks are lightweight, low density, lighter colors mostly. Okay? Then you get into heavier rocks that are solid rock. Then you get into heavier rock and heavier, and then finally you get to a molten core. So the Earth is not uniform distribution of anything. The innermost core is, well, I don't want to say that. The core is mostly molten, meaning melted. Now, why would it be melted? Certainly not melted from the heat of the sun, because it's way, 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 way deep in the earth. But it's melted because all of the pressure of everything above it is pushing in on it. Gravitation is pulling in, and what happens when you rub your hands together? Now, if you rub them together and they're not touching very much, they don't feel anything. But push them together and rub them, and what do you notice? They get hot. And that's because of friction. Well, the molten core has so much weight, frictional force on it, and the objects are moving, and they get hotter, they move faster. That's why the core is molten. It contains most of the heavy elements. Who knows what's all down there? I mean, there may be large deposits of uranium, but we can't get to it. Okay, it's melted. Most of that core is iron and nickel. Okay, iron is the ultimate element formed by fusion, regular fusion. Okay, all the smaller ones keep combining. If you get more and more fusion, till you get the iron, but after that, they don't do it normally by fusion anymore. Okay, nickel is right next to iron, so it's pretty close to it. Okay, now iron has made its way to the surface. That's why we have iron ore in Birmingham and Bessemer and various places, because some of that does make its way to the surface. You don't have that many nickel mines because nickel isn't as prevalent as iron, and it just doesn't seem to come to the surface much. Okay, so there's the molten core. There's also a thin, very thin surface crust. That means only a few miles thick. So that sounds thick to me, but that's really thin. These are mostly lighter elements. Okay? So much so that 8 elements make up about 98.6. You have almost the whole crust. 8 elements. And here's what they are. Okay? First of these is the Earth's crust. Now wait, we're talking about solid Earth materials here, aren't we? How is it that oxygen is almost half of the Earth's crust? Does that make sense? We're not talking about the atmosphere. We're talking about solid materials. Someone name a rock or a mineral that you know. Any solid thing that you know. Name one. You go to the beach, what solid particles get in your shoes and hurt your feet? Sand. What is sand? It's silica oxide. It's silicate. Si, silicon, that's a solid. O4, 4 oxygens are mixed with every one of those silicas to make that sand particle. So 4 times, well, not quite, but yeah, close to it. A lot more oxygen there than there is silicon. Okay? So that's why. How about limestone? Calcium carbonate. More oxygen there than calcium, more oxygen there than carbon. Okay? 3 oxygens for any one carbon, any one calcium. Everything just has so much oxygen combined with it. So that's why the oxygen is part of the solid Earth materials, because it's in there as compounds, as minerals. Almost half of the Earth's crust is made up of some sort of thing combined with oxygen. Silicon is the most common. That's a little over a quarter of the Earth's surface is made up of silicon. Okay, mostly combined with oxygen, but more oxygen than silicon, so that's why there's almost twice as much oxygen in silicon. After that, aluminum. How much pure aluminum? Very little. How much aluminum hydroxide and aluminum oxide? Lots of it. So there's oxygen in both of those. Next is iron. Now, we do have iron deposits on the Earth, surface of the Earth, and not just pure iron. Every bit of red clay you see out there has some iron in it. That's what makes it red, by the way. Okay? So iron is about 5%. Calcium, as I mentioned, most of your limestone is calcium carbonate. Okay? So calcium with some carbon, but lots of oxygen. You also have calcium sulfates, calcium, sulfur, lots of oxygens. You have calcium, just calcium hydroxide, calcium oxide, calcium in many forms. Just about every one of them has oxygen associated with it. There's sodium, and most of that sodium would be in the form of sodium hydroxide, sodium something else. None of it is pure sodium. It just doesn't exist. It combines with something, mostly oxygen. Potassium, right after sodium, very close to it. And again, very little pure potassium, but it's combined with other things. Okay? Potassium, silicate, potassium aluminate. You know, aluminate, I just said it, that's aluminum with oxygen. Oxygen is combining with just about everything. Magnesium, just like calcium, magnesium carbonate, magnesium sulfate, magnesium hydroxide, magnesium something, every one of those that I mentioned has oxygen. And then all the others is about 1.4%, 98.6% plus 1.4, that makes 100%. So almost half of the solid Earth's crust is oxygen, a little over a quarter of it is silicon, and then your other six top, 1, 2, 3, 4, 5, 6, they make up 98%, almost 99% of the crust. Now, that's just the crust. The whole Earth, which involves everything beneath the crust, which would be what we call, we'll talk about this later, the mantle, and then the core. We already mentioned the core. When you combine the whole Earth, then iron moves up ahead, because most of the core is iron and nickel. So iron moves up way ahead of even oxygen and silicon. Oxygen is still very prevalent because it's all over the place. Iron oxide, Fe2O3, FeO. There's iron combines with oxygen. Silicon has dropped down significantly, but still pretty large. Magnesium, amazing, more inside the Earth than on the surface. A lot on the surface, one of the top 8, but really a lot more inside. So iron and magnesium have both grown big time. Your nickel now shows up. Nickel was part of the others down here at less than 1.4%. Now it's up to 2% when you count the whole Earth. Okay? So really when they say iron and nickel, they should have said iron, nickel, and magnesium, because magnesium down there big time too. Okay? Then we have the calcium, which reduced from here to there. Aluminum reduced from that, there it is, there to here. And sodium went from there to here. And now all your others are that. Okay. So the whole Earth, mostly iron. No, not mostly. The largest single component is iron. About a third of the whole Earth is iron. Whereas on the surface, about 5%. 1 part in between. Okay. Does that kind of make sense? So the surface crust, the rocks and minerals make up the solid crust materials. And I've named a few of the compounds that are in those materials. Haven't been really named in the minerals. Silica would be a mineral. Okay. How are we doing? About 10 more minutes, maybe. Okay. Now, you might say, hey, haven't you left off the oceans? They're not solid, and they're not very thick. They're all within the crust. Beneath the oceans is crust. It's called oceanic crust, but it's down there, and that would have iron and all these other things in it. So this diagram is also on page 438 in your text. I think everything's pretty much the same. I don't see any major differences there. All right, so that's the 17.1 solid earth materials. Now let's move into the, just about half of the chapter is going to be minerals. Okay? Now, minerals have a very specific definition. Here's the earth science definition of a mineral. Number 1, it has to be naturally occurring. There's a lab, I guess it's still there, at UAB Physics Department, where they manufacture diamonds. Those diamonds, whereas diamonds are normally minerals, Those they formed, it wasn't naturally occurring, those are manufactured. Okay? That wouldn't be counted a mineral anymore, though it looks just like the other diamond. Inorganic, what does that mean? Inorganic. Anyone have an idea what inorganic means?
From the soil,
Second?
from the land.
Okay, yeah. Basically, it was not part animal or plant before. It was not living before, at least any time recently anyway. So, for instance, the leaf mulch out there that you put around your plants, no, that's not a mineral, okay? That's plant material, okay? Bones would not be minerals. Your teeth would not be minerals. Though they may last a long time and hang around for a while, they are not minerals. So that means inorganic, not recently living material. Solid. To be a mineral, you can't be a liquid or a gas. It has to be a solid. Okay? It can be either an element or a compound. Now, an element, those are elements we saw before. Okay? All these are elements: oxygen, silicon, aluminum, iron, calcium, sodium, potassium, magnesium, nickel. Okay, all those are elements. They are pure. Now, most of the earth materials are not made up of pure anything. Okay, they're made up of combinations, which are compounds, and I was naming those: iron oxide, silica dioxide, magnesium sulfate, magnesium carbonate, nickel. Yeah, they all form compounds. And as I said, most of the oxygen back there, if that was a gas, it wouldn't be a mineral. But it's combined in a compound, meaning they could be made up of, that could be a mineral. And here's the key: with a crystalline structure. Okay? Now, let's take those apart and do them the other way. If they're naturally occurring, they cannot be synthetic. Okay? So we would not count. For instance, the glass in the window is solid. Okay? It's inorganic. It's a compound. But guess what? It was synthetic. Someone took sand, which was a mineral, heated it up, processed it, and made glass out of it. So that would no longer be a mineral. It came from a mineral, but no longer. Not directly produced by a living organism. That's what inorganic means. Must have a regular repeating pattern. That's what crystal is. Now, here's an example: halite. There's a much more common name for halite. What is it? I give it here as sodium chloride. What's that? I bet you some of you use some today. Salt. Table salt is sodium chloride. Now, that may not be the mineral sodium chloride because it's been processed, it's been purified, it's been synthesized, okay? But naturally occurring salt, halite, sodium chloride. Now, here's a diagram of sodium chloride. It's a compound made up of sodium and chloride ions. Now, I mentioned before what an ion is. Anyone remember? It's an atom that is either gained or lost an electron. A sodium ion has lost an electron. A chloride ion has gained an electron. Well, that makes the sodium positive because it's lost a negative electron. It makes the chlorine ion negative because it gained a negative electron. That means they're attracted and held together with an electrostatic bond. That's the chemistry, okay? Won't go into that now, okay? But when they form together to form a crystal halite, here's what a crystal is. Regular pattern. Sodium, chlorine, sodium, chlorine, sodium, chlorine, sodium, chlorine, sodium, chlorine, sodium, chlorine. Always repeating a structural unit. These units are little cubes. We call this a cubic structure. Yes?
It's 510 right now.
Oh, is it? Okay. So we'll end this slide with this slide, I think. Let me see what the next one is. No, we don't have time to get in the crystal structure. But I'll show you a cubic structure here. There is an error on this slide. Can anyone find it? The golds are the sodium and the blues are the chlorine. Or you might think there's green and blue. I don't know what color they are. Here's the error. That one back there, that should be green, because no sodium is ever connected to another sodium, no chlorine ever connected to another chlorine. These two chlorines are, and those two are both connected to each other. That's got to be and these two are right back there, are connected. They can't be. That has to be a chlorine. A sodium. So that should be green. Okay. Good deal. All right, we will stop there and pick up right after that. What was the next slide? The crystal structures. There we go, right there. All right. Now, so let me end this. Does anyone need this left up there a little bit longer? Everybody got it? Okay.